The thief wants to maximize the dollar value of the stolen goods, okay? But making sure that the weights of the stolen goods are less than or equal to the maximum weight capital W, all right? And each item, the thief has the choice of either take the item or leave the item. Okay, so the idea here is, can I choose a set of items I sub 1 through I sub k such that summation W I j, j going from 1 to k, so the sum of all the stolen items is less than the weight capacity, and the value that I get is maximized. Okay, and this problem is called the knapsack problem. Okay, choose a subset of these items. Every item you choose it or you leave it, and choose a subset of these items so that the sum of the value of the stolen goods is maximized, whereas the weight of these items, the sum of the weights of the chosen item is less than equal to the capacity of my knapsack. All right, so when you think of such a problem and you think of the rather funny way that it's formulated, okay, assuming that being robbed is actually funny, all right, which I apologize if you have been robbed before, but the idea here is algorithmists, they like to have some fun at our expense, and here is some fun at our expense. But the underlying problem is a serious problem. This is a problem that keeps coming up in a lot of places. Okay, this comes up because we may have a set of options of shares that we want to buy. We may have a price constraint, and we may simply say, okay, this is the budget. So this is the budget. We may either choose some of these shares to buy and some of these shares not to buy, and for each of them we may have an expected revenue and we want to maximize the revenue. So this is not an uncommon problem in more serious situations, but it's been framed as if we are helping a thief. But remember, that's just fun. Algorithms is not about breaking the law. Algorithms doesn't help burglary, but we are framing it as a droll instance or a funny instance, and sometimes people doing algorithms can be funny. All right. Okay, so the idea here is we are going to come up with a dynamic programming algorithm. So let me recall from the previous lectures some of the steps of dynamic programming. The first step is ID the optimal substructure in the problem. Number 2, make up a recurrence for the revenue or profit. And we have a name for this. This is also called the cost to go function or the value function. So make up the value function. 3, memoize to solve the recurrence, build a memo table. And 4, recover the optimal set of choices. Okay. So this is the 4-step paradigm, and once you master this 4-step paradigm, life is easy. Life is easy. All right, so let us start with the very first step. Number 1, ID the optimal substructure. All right, that means that we have to recognize that this problem is maximization or minimization. It's a maximization problem. Very good. All right, because we are maximizing, we are helping the thief, and the thief wants to maximize. Okay. And if you want to feel good about yourself, think of this as a Ocean's 11 situation, Ocean's 11 movie situation. The thief has been wronged and is out to get revenge. No, that doesn't justify breaking the law. We could have this debate ad infinitum, but let's keep going. All right. So what is the decision sequence? So is there a sequence of decisions being made here? Sequence of decisions. Can we think of it as a sequence of decisions? Yes. We can think of it as a sequence of decisions as follows. For each item, let us visit it from 1 to n. So let us visit the items from 1 to n. In serial order, and for each item I have two decisions: take it or leave it. That's it, right? I have two decisions. So this is good. This means that we can stage the decisions. We can stage the decisions. And here is where you should be thinking back to the two previous algorithms we have studied: rod cutting, coin changing. And you have to think about how did we stage the decisions in those two previous settings. Does this make sense? All right. And now let us ID the optimal substructure. Let us actually convince ourselves that there is an optimal substructure here. And what is it? Suppose for some item j, I commit to, let's say, taking it. Then what is the remaining problem? The remaining problem is the remaining items. So the items, you have to make a decision for items j plus 1 to item n. Okay, so here we are staging the decision. So let's say we are committed to making from item 1 to item j. Okay, that the prefix part I'm not saying, but that's how the algorithm will pan out, as you will see in a second. Okay, now I have to, this is to do, to make a decision. All right, and so far what does it mean? It's an example of a same sub problem. What is happening? So suppose the weight, capacity weight is w, that is the weight remaining so far. All right, and so what is the idea here? So the idea here is when I choose item j, my remaining capacity is w minus wj. Okay, wj has already been put in the knapsack, so it's now capital W minus wj. So I have to find, this is my new capacity limit, and these are the new items available to me, ij plus 1 to in. These are the items that are available to me, and let me try and maximize my profit. Let me try and maximize my profit. What if I leave it? Well, if I leave it, then my remaining items are items j plus 1 to items n. I have already decided to throw away item j from consideration. I am not interested. The remaining capacity is still capital W. All right. So in each case, if I decide to take it or if I decide to leave it, what remains is a sub problem that looks like the original problem but with different data. And by solving this little sub problem optimally, I can augment it with my decision here to make a decision for everything from ij to in. All right. So you have to remember, this is what it means to ID the optimal substructure. So when I ID the optimal substructure, I have decided on a sequence of decisions. How am I going to sequence up my decisions? I have decided I'm going to go from 1 up to n. I could have decided to go from n to 1. I did not do that. I decided, I convinced myself that if I commit to a decision so far, then what remains is an instance of the same problem. Okay, number 2. Number 3, by solving that sub problem and tacking on the solution, I get a solution for the original problem. All right, and that would be optimal. If I solve the sub problem optimally and tack on the solution, I end up solving the original problem optimally. Okay, and that means I have ID'd the optimal substructure, and this process allows me to write down a recurrence. Okay, so let me write down the recurrence. What do I write down a recurrence for? So remember, there are two things we want to find out. One is, what is the maximum value that I can obtain, and more importantly, how do I go about, what sequence of decisions do I need to take to obtain the maximum value? All right, so I need to make those two, but we will simply focus on the maximum value. So we will be calling it max value. Okay, and I will have to talk about what are the items that are left over. Since I'm staging the decision from 1, 2, 3 up to n, I can say what is the current item that I'm considering. Okay, so considering I have taken care of making choices up to item j minus 1, considering item j onwards, what is the max value that I can get. I forgot, I have to track the current limit. So current limit, capital W. So if this is the current capacity limit, this means that by putting j here, the meaning of this is that ij to in, the suffix from ij to in, are available for my consideration. So what is the idea? So this is the idea. Okay. What are the base cases I have to think about? So the first base case I have to think about is when W equals 0. That is, there is no capacity left. If there is no capacity left in my knapsack, the value that I can get is 0. Make sense? If there is no capacity left, my knapsack is full. I cannot get any more value. I am done. What if my capacity left is negative? So what if I have negative capacity left? That means that I overfilled my knapsack. If I overfill my knapsack, that's bad. My knapsack is going to tear and spread items all over the floor. It's going to make a sound. I am going to get caught. I am going to go to the jail. Well, I'm not the thief. When the thief is going to get caught, the thief is going to get to the jail. I am the professor, of course. I'm not the thief. Okay? All right. With that being said, what should the value be when W less than 0? Well, I should be punished, or well, the thief should be punished and sent to jail. That means that if I am maximizing, I have to give it the worst possible result, and that should be negative infinity. A very, very, very big magnitude, but negative number. All right? Be careful. All right. If it's max, it has to be negative infinity to punish. If it's min, it has to be positive infinity to punish. Now comes the recursive part. So these two were the base case. Now comes the recurrence part. Well, it's going to be, I have two choices. I can either take the item j or leave the item j, and whichever is bigger, I will take it. So if I take the item j, I get the value of j plus max value of j plus 1, because everything from 1 up to j have all been taken care of. So j plus 1 is the next item to be taken care of. Okay, and what? And W minus Wj. Okay, or this is for take it. What about leave it? Well, if I leave it, I don't get the value of the item. I have discarded the item. So if I leave it, I simply get max value of j plus 1 comma W. Because I don't put anything in my knapsack, my capacity remains W. And by the way, that means that I also need one more base case. And this base case, I have assumed that j plus 1 is not going to go past n, which means I still have items left. So I need one more base case. So let me insert one more base case here. So if j equals n, okay, if j equals n and W greater than 0, which means that, or j equals n plus 1 really, because j equals n literally means that the item n to item n, which means item n is under consideration. I'm still using pseudocode notation, right? So j equals n plus 1, W greater than 0. Why not W less than 0? Well, that's already taken care of. This is for any j. This is for all j, for all j. Now this is going to be for j equals n plus 1, but I don't need to fall under these two cases. So W greater than 0. Well, what does it mean? I have capacity left in my knapsack, but I don't have any items left, which means that I don't get any value. So this is yet another base case. I forgot, but this has to be yet another base case. All right, so we have the recursion. Let me go through the recursion again. So the recursion is called max value j comma W. This means that what is the maximum value that I can get considering all items from ij all the way up to in inclusive. W is my current capacity limit on my knapsack. What's the maximum I can obtain in that situation? Well, it's 0 if there is no capacity in the knapsack. It's minus infinity if the capacity of the knapsack is negative. And you have to go back to rod cutting and coin changing to understand when do you exactly end up in the situation. And you end up in the situation when you have over capacitated your knapsack, when you have filled up your knapsack and gone over, which is bad. It's not allowed by the problem, so punish, which means to punish something where you're maximizing, you put in the smallest value possible. Another base case is when you have run out of items, j equals n plus 1 and w greater than 0. Because I have already considered these two base cases, I simply need to consider w greater than 0. Well, then the value is 0. If I don't fall into any of these base cases, I fall into the recursive case. So either I take item j or I leave item j. Just like when I did the optimal sub problem, I showed you how I staged the decision. The recurrence has to reflect the way I staged the decision. If I take item j, it's v sub j plus max value j plus 1, w minus wj. Why j plus 1? Because item j has already been taken care of. Next item to take care of is j plus 1 in our sequence. Why w minus wj? Because w used to be the capacity of the knapsack. I added an item with weight wj, so it's w minus wj. So if I take it, otherwise it's max value j plus 1 capital W if I leave it. All right. Hopefully this part is clear, and if this part is clear, congratulations, we have gone past the second step of dynamic programming. All right. So now board is full. Time to clean things up and take this recurrence, memorize this recurrence. Once we have memorized this recurrence, talk about how are we going to recover the optimal set of choices. Okay, and to the third step where we are going to memorize this recurrence. All right. So what are the inputs of the knapsack problem? The maximum capacity constraint W, and you have for each item 1 to n, you have the weight of the item and the value of the item. And there are n items. All right. And so the recurrence we derived was max value j comma capital W is all of these things. So how do I memorize these recurrences? Now this is interesting because now we have two arguments to the recurrence, j and w. J goes from 1 all the way to n plus 1. Okay, n plus 1 being the base case. W, the second argument, okay, let me call the original capacity W sub 0. So W goes from 0 all the way to W sub 0. Let's call the original capacity at the very beginning with the empty knapsack W sub 0. So it goes from 0 all the way to capital W sub 0. All right, so how do I memorize? So instead of designing an array, now I have to design a table. The rows are going to be from 1, j equals 1, to j equals n plus 1, j equals n. Okay. And w starting from 0 all the way to capital W sub 0. All right. Now how about the base case? Well, when w equals 0, this is all 0, so I can fill this out. When j equals n plus 1, this is all 0, so I can fill this out. All right, the two base cases. And this base case, when w less than 0 minus infinity, I will just keep it in mind because I can't put it in a table because minus infinity means like a lot of rows or a lot of columns which I won't put in the table. All right, now the idea is very simple. My interest is in computing the entry here. So I am very interested in max value of 1 comma capital W0. That is what I'm interested in computing because that gives me what's the maximum value I obtain considering all items from I1 through I sub n with a capacity initially of W sub 0. So I am very interested in the entry here. All right. Now what does the recurrence look like? The recurrence looks like this. So max value of JW depends on j plus 1 and either w or something smaller. So if I'm interested in filling up some row, like right here, then I have to look at one row like this at the same weight, or one row with a smaller weight. So I'm always looking at one row below. So if I'm interested in knowing the value at some j, the next value the recurrence looks at is j plus 1 right here, and then looking at the w, the recurrence looked at either w minus w sub j or w. So it's either looking at w minus w sub j or w itself. All right. So this is the idea. So I'm either going to look like this or like this. So how do I fill up this table? All right. So if I start filling up the table like this, for each row I start filling it up from left to right, and then I go from bottom to top. So I go from, for j equals n all the way down to 1, for w equals 1 all the way to capital W0. And by the way, I assume that this W1 through Wn are all whole numbers. If they are fractions, you have to scale them by their greatest common or by their least common multiple. Okay, you have to scale all fractions by the least common multiple to make all the W whole numbers. Okay, let's assume you do that. So n going from, for j going from n down to 1, w going from 1 to W0. So you're filling up the table from left to right, from bottom to top, because an entry at some point in the table depends on things below and to the left, So therefore, the table has to be filled in this very specific order. It can be flipped, so you can fill it from left to, bottom to top and left to right. So you can interchange the order of these for loops, but this is important. You have to go from, each time you have to go from left to right. So this is going left to right, and this is going bottom to top. All right, and then what? And then I'm going to implement this. So I'm going to say T of j w equals, okay, max of T of j plus 1 w, so this case, or T of j plus 1 w minus wj plus vj. So just implement this recurrence, except that instead of calling max value, I'm just going to fetch the table entry. All right, and the final value is return T of 1 capital W0. What's the running time of this algorithm? The running time of this algorithm is n times, okay, it's theta n times W0. But unfortunately, remember, W0 is the actual magnitude. So for example, if the weight was W0 equals 10,000, then that is being represented by 1, 2, 3, 4, 5 decimal digits. But this is going to be roughly 10 to the power the length of W0. So length of W0 is the size of the encoding. And since complexity is always the size of the input, even though the size of the input here is 5 digits, the number of times the algorithm runs is proportional to 10 to the 5. If the size were 6 digits, the running time of the algorithm is 10 to the 6. So what happens is algorithm looks polynomial, and it's called pseudo polynomial in W0, but it's actually exponential in capital W0, which means that in terms of the size of encoding capital W0, this algorithm runs in exponential time. Okay, and that's bad news. All right, and as you will see towards the end of this course, trying to find an efficient algorithm for knapsack for large values of W0 is equivalent to a 50-year-old, 60-year-old open question called the P versus NP question. All right. Hopefully this is clear. Now the last question I have for you is, can you think of how would I recover the solution? All right, how would I recover the solution? To recover the solution, remember, I have to make an additional notation. This additional notation that I make at every point is to tell you which of these two options won out. So even though it's the max of two options, I have to record which of these two options won out. So for that, we can use a secondary table called the S table to record the solutions. All right, and at each point in the S table, I'm going to record one of following. So I'm going to record either take or leave. Okay, so I will record one of two characters. I can put 0 or 1, take or leave. 1 bit is all I need. So I record which one of the answers won over. All right, so finally, to reconstruct the solution, I start from the right hand corner here, and then I see whether I should take item number 1 or leave item number 1. If I take item number 1, put item number 1 in my knapsack, and then my remaining capacity is updated to W0 minus W1. So then I go to j equals 2 with that capacity. If on the other hand I leave, I simply go to j equals 2 with the original capacity. So now I either look at this cell in the table or this cell in the table, depending on the decision I made at the very first cell. If I decided to take, then I go to this cell. Now here, if I decided to take, then I would go to this cell, right? So this gives me a sequence of decisions that I made at every step, so I can reconstruct that sequence of decisions until I either end up on this row or I either end up passing through the end of the table. Once I do that, I stop, and that gives me the sequence of decisions I made. All right, I will post the notebook which has all the algorithm, the Python code for the knapsack problem, for the simple version of the knapsack problem. So you can run it with some inputs, and you can also see how it reconstructs the decision. All right, thank you. Hope you will be able to play with it and understand this algorithm better. About one very confusing aspect of dynamic programming. So we often talk about the optimal substructure, and that's the very first step of dynamic programming, is to look at the optimal substructure of the problem and decide that it has optimal substructure and so on. But remember, not all problems need to have optimal substructure. Sometimes you can pose problems in a complicated way, or even simple problems that fail to have the optimal substructure. And in those cases, dynamic programming is not going to give you the best solution. It's not going to work. Let's take an example. So let's take some examples where there is no optimal substructure. All right, let's give you some simple examples first. So we already looked at knapsack. Okay, so let's take a version of knapsack. In knapsack, there is a weight capacity, capital W0, and you have some items of weight W1 through W sub n and values V1 through V sub n. Okay, so you wanted to either take items or leave items such that the sum of the weights of the taken items must be less than or equal to the capacity, and the value must be maximized. Okay, so we saw that this problem had the optimal substructure by committing to a choice up to whether to take or leave items up to j. Then by committing to a particular choice for j plus 1, you can either take it or leave it, and then you have two types of remaining problem, either with capacity w minus wj plus 1 or just w, and you're looking at j plus 2 to n. And if you solve these problems optimally, you can solve them, tack on the original solution, and you can be done. Now let us look at a strange version of knapsack, okay, that does not necessarily have the optimal substructure. At least the way we are going to state it, it may not have the optimal substructure. All right, so here is the idea. So the idea here is the value v is no longer the sum of the values of the individual items. The value v is actually going to be in this version of knapsack. So value v is going to be the sum of the items Vij that are chosen if the number of items I chose in my knapsack was less than 10. But if I chose more than 10 items in my knapsack, my value was simply let's say Vij times 0.1. Why is that? Okay, you imagine a thievery situation where let's say there is a fence, a person who sells the goods after you have stolen them. Well, not you, but the thief has stolen them. And let's say the fence is very clever that if the thief stole less than 10 items, then the thief can pretend that those are belonging to the burglar and sell them to a proper shop and therefore gets full value. If the thief stole too many, then the thief can no longer do that, and let's say the thief has to sell to a fence and therefore does not get full value, only gets 1/10 of the value. A problem like this cannot necessarily have the optimal substructure. At least the way we are sequencing the decision may not lead to an optimal substructure. So how did we sequence the decision? So we sequence the decisions like this. Suppose I made decisions for items 1 through items j. Then for item j plus 1, I can either take it or I can leave it. And the remaining problem is to solve for items j plus 1 to n. If I took it, the remaining capacity is Wj. If I didn't take it, the remaining capacity is W. If I found optimal solutions for either of these, whichever one is better, I take that decision, I sequence it, I tack on to the original decisions, plus my new optimal decision gives me the optimal decision for the whole problem. We saw this in the previous lecture. But in this case, unfortunately, this structure doesn't hold, because it may be the case that I have already chosen 10 items. Okay, and if I've already chosen 10 items, then by solving this problem optimally doesn't mean I can tack on the solution and get a solution to the original problem. It may be the case that by the nature of the solution here means that I have to re-examine how I solve this original problem. So I cannot, in this particular example, sequence the decisions like, let me make a decision for 1. Knowing the decision for 1, let me solve the sub-problem for 2 up to n, take the decision for 2 up to n, tack on the decision for 1, and voila, I get the best answer for the whole problem. Not going to happen. The recurrence is not going to be as simple. And this is an example where the optimal substructure does not hold. At least it does not hold the way I have sequenced the problem. I hope this is clear. Let me take another example. Okay, so in this example, let us say that I am in a maze. Okay, each step I can go right or I can go up, and my goal is to go from 1, 1 to n, n. And let's say there is a cost for going up each time, there is a cost for going right, okay, and these are different, and so on. All right, I can go down, so there is cost for every move. I can go left, I can go right, and so on. And now I have to find the longest route from 1, 1 to n, n, but I cannot revisit a point that I have previously visited. I can't circle around, because if I can circle around, then the longest route is very, very simple. It's just keep circling around and never reach n, n. No, I'm not allowed to do that. I need to go from 1, 1 to n, n, and I have to take the longest and the most circuitous route. All right, and by the way, I cannot revisit a node that I previously visited. So that is the problem. All right. Let us say I am at 1, 1 and I have two choices. Let's say I can go up or I can go right. All right, I can also come down. Okay, and let's say it's the same path. I can go left. Let's say it's symmetric that way. All right, so there's a bunch of edges here. Okay, so let me sequence the decision like this. Let me make a decision from 1, 1. I have two choices. I can either go up or I can go right. If I go up, if I go up, then I end up at 1, 2. If I go right, I end up at 2, 1. All right. Now I can separately ask, given all of this, what's the longest path to go from 1, 2 to n, and it may be the case that this longest path will involve going back to 1, 1. So therefore, by separately considering the decision to go up and separately considering the optimal solution from 1, 2 all the way to n, I unfortunately do not, just adding up current decision plus optimal solution from 1, 2 is not the same as longest acyclic path from 1, 1. Because if I don't consider the fact that I've already visited 1, 1, I will be forced to visit it back. Okay? So this way of sequencing the decision does not work here. So again, there is no optimal substructure the way I have sequenced the decision, or there is no optimal substructure the way I have sequenced the decision. So you have to be careful. You really have to consider the first step, and it is often a challenging step, but here is the thing. If you solve enough problems in dynamic programming, this challenging step becomes easier over time. And so I hope you are paying attention to that, and I hope you solve lots of dynamic programming problems, get lots of practice, and by doing so you will find it gets easier to identify, to get the spidey sense of when can you apply optimal substructure and dynamic programming and get it to work, and when do you need to hold back and say, hey, it's not working. All right. Hopefully this is clear, and then let's move on and see one more, maybe a couple of more examples of dynamic programming coming right up. Okay, so we are going to look at the longest common subsequence problem. Okay, now this is a very, very important problem, and it is solved a lot for computational biology, where it gets used in aligning gene sequences and other applications. I'm not myself a biologist, but I know it's very, very commonly used. All right. The problem itself is very simple. Suppose I'm given two strings, S1 and S2. All right. For example, let's call S1 the string okay, let's say that is the string S1, and let's say S2 is all right. They don't have to be the same length. All right. Now the goal here is I want to find places in the string where the same elements occur. So, but I want to go farther than that. So I want to find the longest possible common, in this case, substring. What is that? So I want to find a string. For example, here CTG T A and let's say A. So if you take the string CTG A T A, okay, and I'll show you the positions that got matched. CTG A T A, CTG A T A. So you see is a common substring. It's a substring of both S1 and S2. Now the goal here is to find the longest such string that is in common. And what is the longest such string that's in common? And if you think about it, I kind of designed it this way, but let's do this. So the longest common substring here is going to be CTG A T T A C. Okay, I believe that's a longest common substring. I mean, there are multiple of them, but this is going to be the longest. So the longest one is going to be CTG A T T A C is the longest. Definitely it's a better solution than the previous one. This only had 1, 2, 3, 4, 5, 6 characters. Now this has 1, 2, 3, 4, 5, 6, 7, 8 characters. I wonder if there's anything longer than 8 characters that's a common substring of both S1 and S2. So the problem here is to find the longest substring that is both common to S1 and S2. So maximize the length of the string such that S is a substring of S1 and S2. All right. So this is the problem. Okay. And let us say S1 has length M and S2 has length N. They don't have to be the same length. All right. So what is the idea here? We are going to solve it using dynamic programming. Of course, that's the week that we are in. So we are going to solve it using dynamic programming. So first, I have to ID the optimal substructure. So I have to tell you where is the optimal substructure in the problem. And before I do so, I have to tell you how do I sequence the decisions, right? So how do I sequence the decisions? So suppose, for example, I have these two strings A, C, T, G, G, A, T, T, A, C, A, and C, T, A, G, C, A, T, C, T, A, C. Bear with me. All right. And suppose I have decided on some matches. So suppose I have so far decided to match C with C, T with T, and let's say G with G, and let's say I have also decided to match these two A's right here. So I am here so far. Okay, and these are the decisions that I have made so far. Then if I can take the remaining substring and find the longest common substring between TTACA and TCTAAC. So if I can find these two strings and find the longest common substring, okay, so whatever it is, let's say it was TTAC is the longest common substring between these two. I take this longest common substring and tack on the decisions made so far, CTGA plus whatever the longest common substring is, gives me the longest common substring for the whole problem. All right. So the idea here is this. The idea here is if I have made a decision of matches so far, I am left with whatever is left of string 1 and whatever is left of string 2. So I'm moving from each string from left to right, and I'm considering substrings or I'm considering suffixes and prefixes. So if I chose a prefix of the first string and a prefix of the second string, and I have committed to some matches so far, I've committed to match these two, I've committed to match, I've committed to match, I've committed to match. Remaining TTACA on the first string, TCTAAC on the second string. All right. Now if I can solve the sub-problem for these two and get the longest common substring, then I go back and tack on the matches for the original string and I get back my answer. Okay, this is the optimal substructure. All right, it's a little bit more challenging as an optimal substructure than the previous ones. Okay, in the previous ones, I think the optimal substructure was easier. Here, the optimal substructure is a little harder to see. Let me try it one other way. Okay, so let me give you another way of looking at the optimal substructure. And here is the idea. Here is the idea. All right. So the idea here is as follows. I haven't told you how. I mean, so in this idea, it's going to give you the same answer. It's going to give you the same answer, exactly the same recurrence. But maybe it's a clearer way of showing you the way that I have sequenced the decision. All right. So here, let me do the following. Let me take these two strings and let me put my finger on each of these strings. So I have my first string. Okay, and I have my second string. Let me place a pointer or my finger on positions on the two different strings. Let me call the index where the pointer is pointing to the first string as I, and let me call the index where I'm pointing to the second string as j. So this is index 1 all the way up to index m, index 1 up to index n. All right. So wherever I'm pointing, let me call that I and j. Okay. So here in this case, I is pointing at G and J is pointing at A. All right. I have three choices. Choice number 1 is match the two characters where I am currently pointing. Hold on. This is not possible. I cannot possibly match G and A. Right? If I match G and A, that's wrong. I can only match G with a G or A with a A, T with a T. So this is not possible, but let me write a caveat if the first string at position I equals to the second string at position J. If they are the same, then a match can be concluded. If they are not the same, then this option doesn't exist. Okay, so this option comes into play only if the two strings are the same. Or second option is advance I to I plus 1, which means in this case, what am I doing? I'm giving up on finding a match for S1 of I. The third option is advance J in that case, I remains where it is. I'm giving up on finding for S2 of J. Hopefully this way of framing the problem is better. I have one of three choices. Either if I am pointing to the same character where I am pointing right now, if they are the same character, match them and move on. So in that case, what happens is I will move on to I plus 1, J plus 1. Or else keep the character for S2 the same and move on one step on I. Or keep the character for S1 the same and move on one step for J. All right, so this is going to be my idea of sequencing the decision. So I have three possible options. The first option coming into play only if S1 of I equals S2 of J. Okay. Now what's the remaining problem? So the remaining problem here, if I end up having to choose the first option, well, I'm going to get 1, which is the match I just made, so that's 1, plus the best option. So the best match is starting from I plus 1 and J plus 1. So I'm allowed to move both my fingers, and if I manage to match the two strings, suppose instead of a G, imagine for a second this was an A, well, I could make this match, and the remaining options are everything that's left over in the first string and the second string. Or if I advance I to I plus 1, sadly I didn't make a match, so here I can only make the best matches from I plus 1 to J. and here it's ij plus 1. All right. So now you can see that there is a way of writing a recurrence. All right. I won't call it best matches, but I'm going to call it the longest common subsequence, LCS. So let me write down LCS of I comma j, and this is step 2, write recurrence. All right. So LCS of I comma j is going to be, what's the meaning of this recurrence? The meaning of this recurrence is what? The longest common subsequence, for the substring, for the suffix s1 of I all the way to s1 of n, the suffix of the first string, and s2 of j all the way to, this is m, to s2 of n. Okay, so this I and j are just denoting 2 pointers, but it's actually denoting the suffix starting from I to the end of the first string, suffix starting from j to the end of the second string. The longest common subsequence of those 2 strings, those 2 suffixes, equals what? So there are some base cases to write down. So the first base case is when I goes past the end of the string. Well, then there is nothing to do. The longest common subsequence is 0. If j goes past the end of the string, so this is m plus 1, the size of the first string, n plus 1, then the answer is 0. All right. If I goes past the end of the first string, answer is 0. J goes past the end of the second string, answer is 0. What else? Otherwise, there are 3 options. Remembering that the first option only occurs if s1 of I equals s2 of j. In that case, I can get 1 plus, okay, so let me write this down. 1 plus LCS of I plus 1, j plus 1. But only if, this term can occur only if s1 of I equals s2 of j. If the characters are the same, that's the only case I can match, then I can move on. Or LCS of I plus 1 j, or LCS of I j plus 1. Okay. If this first option did not occur, then you should not write down this term. Okay. So if s1 of I and s2 of j were not the same, you should not be writing down the first term, because you will end up matching two characters that are not the same. Okay. So in fact, if you think for a second, all right, let us rewind ourselves and think for a second. Suppose I and j were in fact pointing to the same character a. In this case, I can always, without any loss of generality, I can match what is there right now and move on. Okay. The point being the following. If, for example, I did not do that, let's say I instead chose not to make this match, but I chose to make the match of this a to some other a right here. Well, it doesn't matter. You could always have exchanged these, and you could have, instead of this a, you could have made a substitution, you could have made a trade and matched to this a, and it's all the same. Matching against a gives you a 1 to the length of the substring that you match. So it doesn't matter if you match to this a or this a. You might as well match to the bird in hand right now instead of waiting for a future match to come in. So with that in mind, and if you think about it, this recurrence turns out to be very, very nice. So what it turns out to be is like this. If s1 of I equals s1 of j, all you need to do is just do 1 plus this. All right, that's all you need to do. And you just need to do max of this only if s1 of I not equal to s2 of j, and that saves you a little bit of computation. It's still not wrong, and it makes the recurrence much easier. So the answer is 1 plus LCS of I plus 1 j plus 1 if s1 of I equals s2 of j, or max of these two terms if s1 of I not equal to s2 of j. Okay, not equal to and this is S1 of I equals S2 of j. Okay, good so far. All right, with that being the case, let us see how this algorithm can be passed on to the third step, which is design a memo table and memoize the algorithm. Welcome back, and now we are going to talk about how do we memoize, design a memo table to solve the recurrence for computing the longest common subsequence. There are two arguments, I and j, and they range, I ranges from 1 all the way to n plus 1, where the last n plus 1 says I has gotten past the end of the string. So let's call it m plus 1, m being the length of the first string, and j going from 1 to n plus 1, n being the length of the second string. All right. So therefore, the memo table is going to be two-dimensional. It's going to have a bunch of rows I going from 1, 2, up to m plus 1. Let's make them columns for now. You could have made them rows as well. But let's put I along the columns. Let's put j along the rows. Okay. Well, that will not give us I comma j. Well, I comma j means I needs to be along the rows, j needs to be along the columns. Let's make it I along the columns, j along the columns, I along the rows. Does that work? Very good. All right. And the thing that I'm interested in is LCS of ij is the longest common subsequence of the string from s sub I to Sn, from the suffix for S1, S2j to S2 n, this is m. So these are the two suffixes. So therefore, my original problem was to find the LCS of 1, 1, starting from position 1. So I'm interested in filling up this entry. And the base cases tell me that if I have m plus 1, this is all 0. If I have n plus 1, this is all 0. So I can pad it with base cases. Very good. Now what does the recurrence say? So the recurrence says if I am at some position I comma j, right? If I am at some position I comma j, if the two characters at those position was equal, I need to look at I plus 1, j plus 1. All right. Otherwise, if the two characters were not equal, I either look at this value to my right or this value to the bottom, and I take the max of those two values. All right. So given that I comma j depends on things either to the right and bottom, this gives us a way to fill up the table. So how do we fill up the table? Well, we'll always have to make sure that whenever we are at this position I comma j, the three entries to the right, down, and diagonally one position to the right have to be filled up. So to do that, if we fill up starting from right to left, bottom to top, then we are good. So for I equals m down to 1, for j equals n down to 1, okay, bottom to top. All right, what do? I say LCS table of ij equals okay, either like this: if S1 of I equals S2 of j, then score a match. So LCS of ij equals 1 plus LCS of I plus 1, j plus 1. Otherwise, else LCS of ij equals max of LCS of I plus 1j, LCS of I j plus 1. That's it. All right. Now once that's done, when the table fills up and it's done, the return value is LCS of 1 1 at here. Okay. Last step, how do I recover the solution? Well, right, so we have seen how to fill up the table. All right. Now each time I fill up the table, I can have three cases: case 1, case 2, or case 3. Whenever case 1 holds, you remember that at the corresponding positions the two strings have to have the same character, and I have this LCS of ij is 1 plus LCS ij, I plus 1 j plus 1. All right. Otherwise case 2 or case 3. All right. So what I will do is I will record an auxiliary table same size as the original memo table, maybe one less. I just need to do it from 1 to n, 1 to m. Okay. I'll start at 1 comma 1, which is where I want to see the decision, and I will look at what is the annotation at 1 comma 1. If it's either a 1, if it's annotated as a 1, that tells me that there was a match at this position. So I stack on the match to my answer and I move diagonally down one position, I plus 1, j plus 1. I look at what's there. If there is a 2, that means it's telling me to move to I plus 1 j. So it's telling me to move down. Okay, so now I'm going to look at whatever the answer is here, but no match. All right. Whenever I see a 1, there is a match, I move diagonally down. Whenever I annotate with a 2, there is no match, I just move it down, but vertically down. And then if I see a 3, I just move horizontally down, but no match. All right. If I see a 1, I move diagonally down. And so each time I move diagonally down, I see a 1, I count a match. Okay, I count a match, and that I take all the match strings in sequence, and that gives me the longest common subsequence. Okay, I will post a notebook to illustrate this, and hopefully by exploring the code and exploring some examples, you can see how this process works on a Jupyter notebook. Okay, hopefully that's helpful. I will see you in the next lecture. Thank you. Bye. Okay, so welcome to this lecture on greedy algorithms. All right. So last week we have been looking at dynamic programming. Okay, and we looked at some problems like, for example, the rod cutting problem. Okay, so in the rod cutting problem, we were given a rod of length L, and we were given some lengths L1 and prices P1, L2 prices P2, LK prices PK. And we saw that the solution was to carefully consider all possibilities using the optimal substructure property, and we could solve it. And often you might have noticed, if you played around with the code that we provided you, that it was counterintuitive how to solve the rod cutting problem. So the best cut was often counterintuitive. Okay, in many cases it also takes a lot of time. Okay, the amount of time we took was something like theta of L, where L is the actual length of the rod. So for example, if L equals 1000 and that is 4 digits, the amount of time is 1000. If L equals 10 to the 4, that's 5 digits, the amount of time is 10,000. So as you see, the representation length of L, the number of digits or number of bits to represent L grows. By every bit that you grow, your running time doubles. Okay, so this looks like polynomial, like we briefly mentioned last time. It's a pseudo polynomial algorithm. So it's actually expensive. The dynamic programming solution, once L becomes large, it's again going to be expensive. It's less expensive than the recursion because we are memoizing, but it's still expensive because you have to create a table whose size is as large as the length of the array that you're interested in. Okay, so this is where greedy algorithms come in. in greedy algorithms, these are generally very, very fast algorithms to solve the same kind of problems that we typically solve using dynamic programming, which is to maximize or minimize a value function, okay, some kind of value function subject to some constraints, okay, and typically we make the decisions or stage. So you make a decision as to what is the first cut that I make. Once I have made this first cut, I make the second cut. Once I have made the second cut, I make the third cut, and the problem satisfies the optimal substructure property. Okay, all of this you should know from dynamic programming. Now, what is a greedy algorithm then? Well, a greedy algorithm simply uses what is called a local criterion or a greedy criterion to make a choice right now, and then once it makes a choice, it uses the same greedy criterion to make the next choice, and so on. So in the rod problem, for example, suppose I looked at each of these lengths and each of these prices, and let's say I used a metric price per unit length, P1 divided by L1, P2 divided by L2, Pk divided by Lk. So let me, for example, sort all the options using price per unit length. Okay, what is price per unit length? It means that if, for example, let me give a concrete instance. Let us say I am interested in cutting 80 centimeters, that's the size of the rod that I have to cut, and my length L1 is 45 centimeters, and it fetches a price, let's say, of $4.50. All right, let's say my length L2 is 40 centimeters, and it fetches a price of $3.90. All right, and let's say my length L3 is 30 centimeters, and it fetches a price of $2.50. All right, so these are the three options that I have. Okay, these are the three options that I have for cutting this rod of 80 centimeters. What would dynamic programming do? Well, dynamic programming would carefully build up a memo table of size 80, okay, and it would decide, in this case, I believe the best answer is to make two cuts of 40 centimeters each. So cut L into two sub rods of 40 centimeters, okay, hopefully this is clear. And how much do I get for it? This would pay off $7.80. All right, and that I think is going to be the optimal. All right, but let us look at the greedy solution. So what is the greedy solution going to do? In greedy solution, what we are going to do is we are going to come up with like a metric, some kind of a metric on which we are going to be greedy, and we decided that we are going to be greedy on the price per unit length. So what's the price per unit length? Here the price per unit length is 10 cents for the first option. All right, 10 cents, $4.50 divided by 45 centimeters, so it's 10 cents per centimeter. Okay, so 10 cents per centimeter. I'm not writing the units, you know what the units are. Let me actually make it bigger so you can see it, okay, and bring it here. So for the first option, the price is 10 cents per centimeter. Okay, what about for the second option? Well, it's going to be about 390 divided by 40. All right, something like 975 cents per centimeter. Okay, take my word for it. I might be wrong, but we can fix it later. It's going to be less than 10 cents, that much I know. All right, what's the price per unit length of the third option? Well, for the third option, it's 30 centimeters, $2.50. It's going to be 833 cents per centimeter. Okay, this is okay. I don't need to be precise. If I made a numerical mistake, please point it out on Piazza, and that's okay. All right. Okay. So these are the three options. So in the greedy algorithm, what am I going to do? I'm going to choose Lj that provides greatest value per centimeter or price per centimeter, okay, such that also Lj is less than equal to L. If it were more than L, I cannot cut Lj, so it has to be less than L. Okay, so in this case, I have 80 centimeters worth of rod. Okay, so 80 centimeters worth of rod. So my first decision, according to my greedy algorithm, is choose the one that gives me the best bang for the buck. Okay, literally best price per unit length that I cut, and this is literally L1. Okay, and that says $4.50. So then I'm going to cut off 45 centimeters. Okay, and what remains? What remains is the new L is going to be 35 centimeters after I cut off, and the price that I have gotten for it is $4.50 so far. Now for 35 centimeters, I again apply the same algorithm. Choose the best option that gives me the greatest bang for the buck. But once I only have 35 centimeters, the first two options are out of question, because I can no longer cut a rod of 45 out of 35 or 40 out of 35. I'm only left with a rod of size 30 that I could cut out, and that gives me, that's the best option. In fact, it's the only option. So the second cut, okay, second cut is going to give me 30 centimeters, and then I'm left with 5 centimeters. I have no option for it, so I waste it. All right, so how much do I earn using this option? I earn $7. Okay, so now you have seen your first greedy algorithm. A greedy algorithm is going to be an algorithm that makes choices in a greedy manner. Another word for it is a myopic algorithm. So these algorithms apply when you have to make a sequence of choices. I have to make a choice. Now, based on that choice, I have to make a new choice. Based on that choice, I have to make a new choice based on that choice. In greedy algorithms, I do not do any kind of future look ahead. I look at the set of choices I have. I make up some criterion to choose between them. Here the criterion is my bang for the buck criterion, which is how much cost price do I get per unit centimeter, which is a great criterion, if you will. And I just take the best option that gives me, for now, the largest buck per unit centimeter, which is the first option. Never mind that if I had chosen a slightly less optimal option for now, what that allows me to do is that it allows me to waste less rod eventually, and because I am wasting less rod, I come out ahead eventually. But in a greedy algorithm, I always go with the best option. I cut out that size of the rod. Whatever is left with, I apply the greedy criterion again. I cut out the second best, and then finally I'm left with 5 centimeter waste. Whereas dynamic programming does a look ahead, which means that it's not myopic. It looks forward and says, let me consider the current choice, but based on the current choice, let me look at the remaining subproblem and consider the best way of solving the subproblem. And for all possible current choices, let me find out what's the best way. So that's how dynamic programming works, but it's expensive. Greedy, on the other hand, here is really, really cheap. It's very, very easy to solve this greedy algorithm. It's polynomial time in the size of, it's linear time in the size of L, let's say. Okay, so it's basically an iterative algorithm. It just works a few times, you're done, which is great. But the problem with greedy is that it doesn't always give you the best answer. If you put in more work, you could have gotten a better answer. Okay, so now you have gotten a flavor of greedy algorithm. All right, let's go through some other greedy algorithms, and let's start looking at first examples where greedy algorithms are not going to be the best options. But then strangely, there are some very happy examples, okay, and some very important examples where the greedy algorithm provides you an answer that's as good as a more expensive dynamic programming algorithm. And those are the most important cases. And what are those? So it turns out greedy algorithms are widely used for a couple of reasons. One reason is they are fast. And in many cases, getting a fast answer that's slightly or maybe provably worse than the best answer, it's fine, is better than getting the best answer, which may take a long time to compute. That's one reason to do it. And in some cases, the best option is actually a greedy algorithm. Okay, and these are very, very important cases. So we will look at a few of them today, all right? But then there's more coming up in the rest of this class. More importantly, there is a couple of very, very important algorithms. An algorithm for, for finding minimum spanning trees in graphs, the shortest path algorithm called Dijkstra's algorithm. Okay, among other things, these are going to be well-known examples and widely used examples of greedy algorithms. All right, so we are going to look at a few more examples of greedy algorithms, cases where they are fast but not necessarily provide you the right answer, and then cases where they are actually going to be fast and the happy coincidence of being fast and optimal at the same time, which is everything we want in life, fast and optimal. Okay, so now we are going to look at the greedy coin changing problem. Okay, so we've already looked at the coin changing problem. We have an amount x, and we are allowed coins of denomination C1, C2 through Cn. So for example, you have 78 cents, and you have 1 cent, 5 cents, 10 cents, 25, and 50 cents. Okay, and these are the standard US denominations. It's also standard in many countries, and as you will see, it's standard for a reason. Why? All right, so what's the greedy algorithm for making change? And this is the algorithm that people across the world use for making change. So if I have 78 cents to make for, let me look at the largest coin that still goes under 78 cents. That's 50 cents. So let me first start by giving you 50 cents. So the remaining is 28 cents. Now how do I make change for 28? So I'll give you one 50-cent coin. Now for 28, I'll give you a 25-cent coin. Then I get 3 cents back, and then I'll give you 3 times 1 cent. All right. So the greedy algorithm is the algorithm that millions of people in the US around the world use to provide change. And what is it? Find largest amount C sub I less than equal to C, the amount I have to make change for. Give one coin C sub I, and then recursively solve for C minus C sub I. That's it. So that's what we did here. So if we had to make change for 78 cents, we found the largest amount that goes under 78, 50, give one 50-cent coin. Now we are left with 28 cents. How do I make change for 28? Give one 25-cent coin. Now we are left with 3, and so give 3. And the number of coins we used in this process is 5 coins. One 25-cent, one 50-cent, and 3 1-cent coins. And this is how you would do it in a supermarket or anywhere else. All right. And it turns out that this is actually optimal for these sets of denominations. All right. On the other hand, if I wanted to mess you up, let me introduce, let's say 1, 5, 10, 25. Let's also, for fun, have a 39-cent coin and 50 cents. Why a 39-cent coin? I don't know. Let's say, because we wanted to honor some event that happened in 1939. I don't know, or the 39th president of the United States, whoever that was, let's say they issued a 39-cent coin for some reason. Well, now it's going to mess things up because this is no longer optimal. If I had a 39-cent coin, then the optimal way to give change, which is what our dynamic programming algorithm looked at, was to give two 39-cent coins. And then you have 78 cents and you're done. So instead of 5 coins, I can do it with 2 coins. That's so much better, right? So we have an interesting idea here. If we have the standard US denominations, then greedy algorithm is actually optimal. Okay, so if I had the standard US denomination, then the greedy algorithm is actually optimal. And how do we prove this? This is actually a very, very interesting question. I will not really look into how to prove this for now, but let's say this is a well-studied problem on why this happens. And one hint that I will provide you is, suppose you sum up 1 plus 5, that comes in less than 10. If you sum up 1 plus 5 plus 10, that's 16, which is less than 25. 1 plus 5 plus 10 plus 25 is less than 50. So if you sum up all the preceding denominations, that comes in less than 50. Okay, so that's one good reason why this happens, though that's not the right reason. I'm just alluding to a result about what's known for a knapsack, for a form of knapsack problem, which is what the coin changing problem really is. Let's not worry too much about that. So take my word for it that greedy algorithm is optimal if you had these coins in the standard US denominations, and it's so much faster than the dynamic programming algorithm. On the other hand, if you mess up the standard denomination, then greedy algorithm is no longer optimal. So as we saw in this example here, you can make change with smaller number of coins. All right, so what we have learned from this is greedy algorithms are really great under some situations. They are always fast. Because they are myopic, I'm making one choice right now without consideration of future choices. I'm just making a greedy choice, and then whatever is left over, I solve it using a greedy choice and a greedy choice and so on. They are not always guaranteed to solve the problem. They are not always guaranteed to solve it optimally. But in some instances, they are. And in those instances, they are extremely fast. And as an example, greedy algorithms provide the optimal answer when the coins are the standard US denomination as opposed to some arbitrary numbers we came up with. All right, with this introduction, we are going to look at more greedy algorithms coming right up, where we're going to look at cases where greedy algorithms actually do a great job and actually solve the problem perfectly. All right, coming right up. Okay, so now we are going to look at a greedy algorithm for interval scheduling. All right, so what's the idea here? Let's just say that we have a conference room. All right, let's say we have a conference room, and let's say people would like to reserve some times of the day during which they would like to conference. And let's say every reservation has a start time L1 and an ending time U1. So this is called an interval. All right, and let us say that some of these reservations are conflicting. So what does it mean for one reservation to conflict with another? You can imagine what it means. It means that there is a time overlap in which both meetings want to take place. All right, let's say L2, U2. So this means that they are conflicting with each other. So if they are conflicting with each other, you cannot have both meetings take place because there's just one conference room. All right, and let's say you have a bunch of these requests for using this conference room. Let's call them L1, U1, all the way to L sub n, U sub n. Okay, and I would like to allocate this conference room. So which means that some of these meetings are going to take place and some of these meetings are not going to take place. All right. So I'm going to say yes to some of the meetings, and I'm going to say no to some other meetings. Okay. So I'm going to say yes and no. However, what do I want to do? I want to maximize, and this is super important, the number of meetings. Maximize the number of meetings that takes place. Okay, and there could be other things I could maximize. For example, I could be maximizing the amount of time that the room is occupied. For example, I could be maximizing, suppose each meeting came with a price, like I'm willing to pay $100 to hold this meeting. I'm willing to pay $40 to hold this meeting. And I could say I'm willing to maximize the amount of money I earn from the room by scheduling these meetings. Another example is, suppose one of the meetings is organized by me. Another meeting is organized by a more powerful person, let's say our dean. Another meeting is organized by our director. And so maybe the director and the dean get better priority than me. So higher priority meetings may get more priority than a lower priority meeting. These kinds of problems are called scheduling problems. They don't just have to do about meetings and rooms. They can have to do about jobs that are trying to run on a processor and trying to allocate processing time to jobs. They could be about network bandwidth, things that want to transmit over a network and trying to give bandwidth to these transmitters to transmit their messages on a network. So these kinds of issues happen all the time, and in systems those are called contention issues, where there are many different processes or many different entities that are trying to contend for the same resource, and scheduling is a means by which you are resolving this contention. And scheduling is a huge area in computer science. There are conferences, communities where people are spending their entire time thinking about various types of scheduling problems, and we are trying to scratch the surface by looking at a very simple kind of scheduling. We have one room, just one conference room, and we have some requests that are coming in, and our goal is to maximize the number of meetings that take place, making sure that no overlapping meetings can be scheduled. Okay, so how do we do this? Let's take an example. So let me take time to start from 1. Well, time should start from 0. Let's start it from 0. And let's say time goes to 12. Okay, so these are, let's say, the daylight hours, 0 to 12. So this could be 6 a.m. and this could be 6 p.m. And let's say we have 5 meetings. The first meeting is M1, and they want the room from 2 to 3.5. M2, let's say 3.2 to 4.6. M3, 3.1 to 7.1. M4, 8 to 12. M5, 7 to 8.5. Okay, let's add one more meeting, M6, and they want the room all day. So here is an example of 6 meetings that have coming in. Okay, and I would like to say yes or no to some of these meetings. All right, how should I do this so that I maximize the number of meetings that are held? So for example, if I said yes to M1, and let's say I said yes to M4, and is there anything else I could say yes to? Not really. Okay, so let's say I said M1 and M4. Well, that's one way to do it, M1 and M4. Then I have scheduled 2 meetings, and that's one way to do it. Okay, M4 goes up to 12. All right, I've scheduled 2 meetings. Is there something that I could do which is better? Right? Can I do any better than just scheduling M1 and M4? All right, and that's the big question that we are trying to answer through this lecture on greedy scheduling. All right, so let us take some examples of greedy algorithms that one could think of. So what are the things that I could be greedy on? All right, So what makes sense? So for example, here is one way to approach the problem. Okay, and I'm going to rely on some intuitive arguments here, but you could do things better. All right, so one way is, let's be greedy on meeting size. What does that mean? Let us take, so typically if I want to schedule the maximum number of meetings possible, right, and this constantly happens in supermarkets, right, if you just have one or two items, then people, and you are at the back of the line, some good people who are standing in front of you would say, hey, you just have a few items, why don't you go ahead of me, because I have a cart full, right? So sometimes when you're trying to maximize what's called throughput, or the number of meetings that take place, it may be a good idea to schedule the smallest meetings first, and then worry about scheduling the larger meetings. So maybe let's be greedy on the meeting size. So here is a greedy algorithm. Number one, take the smallest duration meeting, shortest duration meeting, or smallest duration, and schedule it. Number two, remove all meetings that overlap with the scheduled meeting rinse and repeat. Repeat until no meetings remain. Do you think this will work? Do you think this will always give us the best results possible, taking the smallest meeting? It makes sense, right? If you think about the analogy, small meetings take up less time. So if I commit to scheduling a small meeting, then maybe I still have plenty of time left to schedule other meetings, and that's the rationale for it, right? If I schedule little teeny tiny meetings, I have plenty of time left to schedule the other meetings. Is this going to work? Let's take a look at this example. So in this example, what are the durations of each meeting? So this meeting runs for 1.5, 1.4, 4, 4, 1.5, 12. Definitely don't want that, right? All right, so let's look at the shortest duration meeting, that's M2. So let me schedule M2. And that runs between 3.2 and 4.6. Okay, not to scale, not to scale. All right, and once I've scheduled M2, then, well, unfortunately, I can no longer schedule M1. It conflicts with M1. I can no longer schedule M3. All right. And then the next meeting that remains to be scheduled is between M2 is already scheduled. I say yes to M2. All right, M4, M5, and M6. So what's the smallest meeting among these three? Well, it's M5. So let me schedule M5 between 7 and 8.5. Done. Well, that means that M4 is ruled out because it conflicts. M6 is ruled out. Oh, M6 was already ruled out because I scheduled M2. So it was always between M4 and M5. All right, so now I have scheduled two meetings, which was as good as our original attempt where we ended up scheduling M1 and M4. Okay, so maybe we have something here. So maybe this is our winning ticket. But unfortunately, if you think about it, there are situations where scheduling the smallest meeting might be a really bad idea. So let me explain one such situation, right, where scheduling the smallest meeting will end up with fewer meetings than if you had not scheduled the smallest meeting. So you could be greedy on the smallest meeting. So this is an example of a greedy algorithm, but it's going to be suboptimal. Suboptimal. Why is that? Let me take another example. So in this example, I have the room between 0 and 12. Let's say there are two meetings. Okay, so one meeting runs from 0 to 6. Another meeting runs from 7 to 12. Let's call this M1 and M2. And let's say there is a teeny tiny meeting M3 that runs from 5.5 to 7.5. You see where I'm coming from. So now M3 is like that. So if I went after the smallest meeting, it's obviously M3. It's a 2-hour meeting, whereas the other meetings are 6 hours and 5 hours. So if I schedule M3, then I'm only able to schedule one meeting, whereas if I had not scheduled M3, I would be able to schedule both M1 and M2, and then I get 2 meetings out of it, which is better than 1 meeting according to the metric I have chosen. So therefore, with this example, I have shown that the smallest meeting size heuristic is non-optimal. All right. Maybe let's try one other example. Okay. Now, of course, I don't have to tell you about the largest meeting. The largest meeting will definitely not be optimal. As you can see in the example I presented, the largest meeting is M6. If you schedule M6, it's not going to be optimal. All right. So what would be a better idea to be greedy on? So a better idea would be, let us be greedy on something else. Okay. Let's be greedy on the meeting that ends the earliest. All right. How about that? So let's try this strategy. Let's be greedy. Okay. So this doesn't work. Greedy on meeting that ends first, ends the earliest. How does that algorithm look? Very simple. Let us sort all the meetings from on their ending time. So meetings that on their ending times 3.5, 4.6, 7.1. So then I have to switch places for M4 and M5. Then so if I went with that rule, then I would first schedule M1. Right? I would first schedule M1. I'm no longer going by the duration, so let me remove the durations. And let's say M1 would be the first meeting to get scheduled because it's the meeting that ends the earliest. All right. So let's go with the earliest ending meeting, which would be M1, and let's schedule it. Okay, let's schedule it. Now, if I scheduled M1, well, I can no longer schedule M2. I can no longer schedule M3 because they overlap with M1. So let me throw them away. Now let me look at the remaining meetings and then schedule the earliest ending meetings among the remaining ones. So now M5 gets scheduled, okay, between 7 and 8.5. Now once M5 gets scheduled, I throw out M4, and remember I have to throw out M6 because M6 already conflicts with M1. So I end up scheduling M1 and M5, which gives me in this example 2 meetings that I can schedule. All right. So here, if I go greedy on the meeting that ends the earliest, the algorithm is very simple. Sort all the meetings by their ending times, which means by the ending times, sort them in ascending order. Schedule the first meeting, delete all meetings that overlap with this meeting that you just scheduled, and then rinse and repeat, which means of the remaining meetings, take the first meeting, the meeting that ends earlier, schedule it, and then rinse and repeat. As you go through this process, what you would end up is proving that this is actually the golden winning ticket. So this gives you optimal number of meetings. Okay, now that's very surprising. Okay, it's not easy to see, but I'm going to convince you in a second that this is going to be how it is. All right, so let us think through this. Okay, so if I schedule the meeting that always ends the earliest, the claim is it's going to schedule the optimal number of meetings. All right, how do we prove such a claim? Okay, now let us say that you are the scheduling expert. Okay, and looking through this problem and using your expertise and your IQ that's in the stratosphere, you have managed to come up with a schedule, and you claim that your schedule is going to be better than my greedy schedule. Okay, my dumb and greedy algorithm, which is always going to schedule the meeting that ends earliest. And so you have given me a schedule for this room. So your given me Li1, Ui1. Let's say that's the first meeting, and then Li2, Ui2, Lik, Uik. So you manage to schedule k meetings using your really superior intellect, and let's say you're not necessarily following the greedy algorithm. Now I come in and I am the greedy. Hopefully there's no one named Gus in the class. Well, I shouldn't make such jokes. I've been told that there could be future students named Gus. I am so sorry. Let me just say I am greedy. So I come in and I look at your schedule, and let us say I go through your schedule, and let's say you scheduled Li1 and Ui1. So let us say that this was actually the earliest ending meeting. So if this was the choice I would have made, let me go ahead and ratify your choice. All right. So let me go ahead and ratify your choice. On the other hand, if let us say this was not the earliest ending meeting, Li1, Ui1 was not the earliest ending meeting. Let us say there is a meeting that ended earlier, and you did not obviously choose that meeting, right? So this is the first meeting you chose in your expert mode. Well, me in my greedy mode, let us say I would have chosen some other meeting. Let's say, let me call it LG1 and UG1. This would have been my greedy meeting that I would have chosen. Well, no problem. Let me, as the greedy person, take away your choice, and slip in my choice, which is the greedy choice. Okay, and now I claim that this meeting, this meeting that I would have chosen does not conflict with any of the remaining meetings. Why is that? The reason is that the meeting that I had chosen is the earliest ending. So which means that its endpoint must come before the endpoint of the meeting that you have chosen, at or before. It could not have been after the endpoint. So therefore, by erasing your meeting, by erasing your first meeting, you as the expert, and adding me as the greedy person's first meeting, I have just done a one-for-one exchange. I have taken away your meeting and scheduled my meeting, assuming they were different meetings. If they were the same, then no problem. We'll keep going. But what I have done is I've done a one-for-one exchange, right? And therefore, what happens here is that the remaining meetings are still valid. They don't overlap. And so I have done this one-for-one exchange. Now let me go ahead and do the same to the second meeting. Now I remove all the overlapping meetings, and then I schedule my second greedy meeting. Well, I can now, using the same argument on the remaining meetings, I know that my meeting, the meeting I would have chosen second, ends earlier than the meeting you would have chosen second as the expert. So now if I do this one-for-one exchange, okay, one-for-one exchange, what have I shown you? I have shown you that my greedy scheduling can one-for-one match the meetings that you have scheduled. All right. So the greedy algorithm can schedule as many meetings as the expert has scheduled, or even maybe more meetings, because there is more free space that's left. The greedy algorithm could potentially schedule more meetings, but I'm not interested in more. I'll assume you're the expert and I'm not contradicting you, but for every meeting you have scheduled as the world's expert on scheduling, the greedy algorithm schedules another meeting that has to end earlier than your meeting. And in this one-for-one exchange, what do I note? I note that the greedy algorithm schedules the same number or maybe even more meetings than the expert. And since I didn't assume anything about the expert, let's assume the expert was optimal, then the greedy is also optimal. So if you have a good strategy, your strategy can be no better than the greedy strategy. That's all I'm proving. And the reason is that by always choosing the earliest end time, what am I doing? I'm making sure that no matter what you choose, my meeting is going to end earlier than yours. So by taking away your meeting and adding the greedy meeting, no harm is done, no overlaps are created, and I can keep going. Hopefully this is clear. It's like really simple once you think about it, but it's also very, very clever, and therefore the greedy meeting that ends the earliest, the greedy strategy on the end times, which means always take the earliest end time and schedule it, that gives me the optimal strategy. No one can do better than that if I am interested in the number of meetings that take place. Now, obviously this is not going to be always good. So for example, if I have multiple conference rooms, okay, that's a situation where this is not going to work in general, as I've stated. For example, if instead of the number of meetings that take place, I am more interested in helping out with the occupancy of the room. Like I want to see that the room is occupied all the time, or I want to minimize the number of amount of time between meetings, or I want to schedule higher priority meetings first, lower priority second, then it gets complicated. Greedy may no longer be optimal, as you can come up with simple examples that prove that. All right. Hopefully this was clear and informative, and I will see you in the next lecture where we'll look at more greedy algorithms. Thank you. Okay, so now we are going to look at something called Huffman codes, and they are related to this area called compression or coding. Okay, so this is not doesn't mean programming. It means this idea of taking a file and compressing it into a smaller file, so that if you decompress or expand, you get back the original file. Okay, and this is called non-lossy compression. All right, examples. I'm sure you've all taken a file and zipped it. Okay, and there are many algorithms, and zip uses an algorithm. It's based on an algorithm called LZW, which I'm not going to talk about. It's an algorithm that's built into zip, and that it uses to compress the file. All right, but what really is compression? What is compression? All right, so first of all, computers can on the hard disk only represent ones and zeros. All right, because they can only represent ones and zeros, and we would like to store let's say Tolstoy's War and Peace. Okay, we would like to store it on a disk. Well, Tolstoy's War and Peace is written in Russian, or maybe translated in English, and it has A's to Z's, space, commas, semicolons, colons, and all the hyphenation that Tolstoy likes to use. It even has capital A to capital Z, but it doesn't have ones and zeros. So how do we bridge this gap between the characters we are using in a text file, let's say, and the way it is stored in a disk? Well, one way is to use something called ASCII. What is ASCII? Well, ASCII is a way of taking a character like A and transforming it into a number. I don't remember off the top of my head what A was. I believe it was the 65, and B is 66, and so on. So ASCII takes every number, every character, and makes it into an 8-bit representation. Okay, and so if you want to think about it, this is 0x41. That's 41 in hexadecimal, okay, to the base 16. When I say 0x, it usually means hexadecimal. This is 0x42, and so on. All right. So so this is an example of how we code up. Okay. And so when we read a file in the disk, we chunk up the file 8 bits at a time. And we read the pattern of characters, and then we say that's an A, that's an X, that's an E, that's a space, that's an M, and so on. All right, so you can chunk it up 8 bits at a time and read it. So if Tolstoy's War and Peace had, let's say, 1 million characters, 1 million letters in it, or 1 million cars in it, then it would take 8 times 1 million bits on a disk. Okay, that's not exactly 1 MB, but roughly 1 megabyte. All right, so that's an example of how we code up for characters as binary sequences and store them on a disk or in the memory as you please, and retrieve them and print them and so on. Very good. But and by the way, what does ASCII stand for? Most people forget this, but it stands for American Standard Code for Information Interchange. Okay, it's an 8-bit code. Its predecessor was something called EBCDIC. If you're interested in history of computation, I know what that stands for, but I don't want to date myself too much. All right, very good. So this is an example, but then what is the question of compressing? So if I had Tolstoy's War and Peace and I sent it to a zip, it's going to give me warandpeace.zip, which is going to be a really small file actually. It will compress it to about 10% of its original size. So it's, let's say, 100 kilobytes. And then if I unzip, I get back my original War and Peace. If I didn't get back my original War and Peace, why would I do this, right? So it makes it much smaller. Why is this even possible? Okay, let's go back to something a long time ago that was realized by Claude Shannon and others long time ago. All right. So one of the question is, what's the information content? So in many instances, you can see that even though there are long words in English, the information, these words don't have as much information content as you would expect. So for example, here's a common game we have played. Let me take a sentence and take away all the vowels from the sentence and see if you can still figure out what am I writing. Okay, what did I try to write? Water is wet. All right, so many of you would have found it very easy to read this sentence, even though I did not add any, I took away all the vowels. And so it's not perfect, but you can see how vowels are adding less information to this sentence than than you would think, right? For example, a language like Hebrew does not use vowels, and it's still a perfectly intelligible language, right? All right, so enough of that. What's the problem here? The problem here is that I am using 8 bits for every letter in English. So for example, E, which is the most popular character in Tolstoy's War and Peace, let's say, uses 8 bits the same as Z or X, which are going to be less popular. There are much fewer words that contain X or Z than E, right? So E is going to be highly frequent, whereas an A is going to be more frequent. The vowels are generally more frequent than the consonants, and some consonants are going to be more frequent than others, right? But I'm giving everyone 8 bits, all right? And so the problem there is I am wasting a lot of bits, and I could have done it with a fewer number of bits. All right, let me take a simpler example than English. Let us say that we had a long DNA string that we had to compress. So let us, instead of English, just take a long DNA string, all right? And in a long DNA string, let us, it has 4 letters, okay? Don't ask me what they stand for, but the letters are A, C, T, and G, okay? Adenosine, something, something, and this is called guanine, all right? And A and T, I think, are pairs, and C and G occur in pairs. All right. Let us say for some reason that I have a really, really long string. So maybe there's some subliminal messaging going on. I'll say no more. All right. All right. So suppose we had a long string. How would you represent it? Well, there are 4 characters here. And if I coded it up as 2 bits per character, okay, so A, let me say 0, 0 is A, 0, 1 is C, 1, 0 is T, 1, 1 is G. Then I'm going to say 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1. So I'm going to write this entire thing in a sequence of 1s and 0s, and decoding is really easy. I just look at these characters in pairs and I read off what they correspond to. Okay, very good. But suppose my string was 1 million letters long, 1 million bases long, then I would have used 2 million bits. All right. Now, can I do any better? All right. Can I do any better than this? All right. Let us say, for example, that A and T were very frequent and each of them occurred 40% of the time. So instead of being equally occurring, let's say A and T were really, really frequent and 40% of the string is composed of A and T. And let's say C and G were quite infrequent. Let's say 5% of the string was composed of C and G. Okay? For biological reasons, I think A and T will occur equally frequently and C and G will occur equally frequently. Okay? And that was one of the clues for decoding the structure of the DNA. I digress. All right. I'm not a biologist and I may be wrong. So let me just leave that alone and let us suppose that A and T had occurred 40% of the time, C and G occurred 5% of the time. It doesn't matter here. If I'm allocating 2 bits per string, then I am getting about 2 times 10 to the power 6 bits to encode this million letter string. All right. Because each of them is getting 2 bits. Now suppose I did something more cleverer. Suppose I gave A 1 bit, okay. Suppose I gave T 2 bits somehow, and suppose I used 3 bits to represent C and G, all right. How can I do that? So let us say whenever I see a bit 0, that's always an A, all right. Whenever I see a bit 1, 0, that's always a T. And then C and G are going to be 1, 1, 0 and 1, 1, 1 respectively. All right. This sounds very, very strange. Why would I do this? But if I allocated this, then instead of writing the string like this, I would write the string as a 0 for an A, okay, 1, 1, 0 for a C, all right, 1, 0 for a T, all right. 1, 1, 1 for a G. So you can see how instead of writing the string in a straightforward manner, I again substitute for each letter its code word, and now I start writing it this way. Now C and G are going to take more than 2 bits, so they are going to get longer, whereas A is going to get 1 bit, right? That I am gaining. So how many bits would I need to encode this 10 to the power 6 letter string? All right. So first thing I would need is for A 40% of the time, I just need 1 bit. So 0.4 times 1 plus for T, which occurs 40% of the time, I need 2 bits. So 0.4 times 2 plus C, which occurs 5% of the time. So 0.05 times 3 plus G, which occurs 5% of the time. So roughly I need 0.4 plus 0.8 plus 0.15 plus 0.15. So 0.3, 1.1. So I need 1.5 bits per character. On the average, I just need 1.5 bits per character. And therefore, this entire million letter string can now be encoded in 1.5 times 10 to the power 6 bits as opposed to 2 times 10 to the power 6 bits. So I'm saving about half a million bits, which amounts to about half an MB, okay, or less than that megabytes, so about 0.5 divided by 8, but it's nothing to sneeze at. I'm saving some space. All right. So now you get this idea that if I take the more frequently occurring letters and somehow encoded them with smaller length strings, and the lower frequency occurring letters and encoded them with larger length strings, I get a compression. Okay, and this is one way of compressing. Now there is a problem. I cannot do this in any way I please. I have to make sure that when I write these strings, there is one unique way to read any string that I'm given. So now that each character has a different length string, decoding can be a tricky business. So there has to be a unique way of reading any bit string that I'm given. So for example, if I'm given the bit string 11011010, 110101, all right, then I need to assure myself that there is exactly one way to read it. So for example, let me look at how do I read it. Well, I look through this and I say 110 matches a C, and then 10 matches a T. 110 matches a C, matches a C, matches a T. Okay, and I can keep going. Let's say this was a 0. 0 here. Okay, matches an A. So as you can see, there is a unique way of reading it, but only under certain kinds of codes. Okay, not in general. So for example, if instead of T being 10, T was actually coded up with 01, then I am in trouble. So for example, if I had the string 0001, 0101, then the question is, how do I read it? Well, if I read it, 0 is an A, 0 is an A, well, 0 is an A, but then I am left with 10, and as you can see, nothing here begins with 10. Everything begins with 11. So I am in trouble. So I am in trouble because I can no longer complete it. But if I went back and said, if I just waited for this 1, then the 01 is a T. All right, T, T. So as you can see, it's not clear that any of these codes will work. Okay, any of these codes will work. And sometimes either it's really difficult, I need a complicated algorithm to read back some kind of word, or it's impossible, or there may be multiple reads. So for example, I don't know, if I had the string 0001110, there could be multiple reads for this kind of a string. All right. So I'm not going to, so for example, I could read this as A, C, or I could start reading it as A, T, and let's say there was another one here, something like this. So 110 becomes a G. So you can imagine how this process gets really complicated. All right. So there is one way of avoiding these kinds of complications. And the one way to avoid these kinds of complications is to do something called a prefix code. Before I do that, let me fix what I did. This used to be 01. Let me make it back to 10. So the way to avoid this complication is to use something called a prefix code. So we are going to look at what is a prefix code and how does a prefix code avoid the kind of complication where if you write down a bit string and your letters have unequal number of bits for it, then how do you read back from a bit string, how do you read back the characters? And if you use a prefix code, then it ensures that even if your letters have different number of bits, there is exactly one way of reading back a properly encoded string. We'll give you a unique and simple way to read it back, and decompression is easy. So once we get there, we can now see how do we find out prefix codes. Okay, so we have seen already that if I committed to different length codes for different characters, like I said A was a 1, C was a 10, T was a 110, and G was a 101, then what results is utter confusion. So if I wrote down a bit string like 110, 110, 110, 101, something like that, then there are multiple ways of reading it. So I could read this as A, G, let's say C, T, and G. So that's one way of reading it. Another way of reading it is T, 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 G. So this is confusion. So I might have encoded T, 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 G, and then my decompression can read it as A, G, C, T, G, and this is not going to work. So certain codes are a no-no. So what makes a code a good code? So what is a good code? In this respect, a good code is one where no code is a proper prefix of another code. So if you look at A and if you look at C, then A is a proper prefix of the code for C. Likewise, the code for A is a proper prefix for the code for T. The code for C is a proper prefix of the code for G. So no code word should be a proper prefix of another code word. And if indeed that's the case, then you can prove that whenever I code up something, when I take a string and I make a code, then decoding it will uniquely give me back the string. There's exactly one way to decode it, and it will uniquely give back the string. Okay? And such a code is called a prefix code. So as an example, this is definitely not a prefix code, whereas an example of a prefix code would be, let's give A the code 0, C the code 10, T the code 110. Like we saw before, this is an example of a prefix code. Make sure that no code word 0 is not a proper prefix of any other code word. 10 is not a proper prefix of the code for T or G. 110 is not a proper prefix of 111. Okay? Furthermore, there is another beautiful property. Prefix codes can be written as trees. So here is an example. So I start with a root node, and the leaves nodes are going to be labeled by characters. So if I have a 0, that's an A. Otherwise, I have a 1. Now, if I have a 1 and a 0, that's a C. Okay? And if I have a 1 and a 1, okay? If I have a 1 and a 1 and a 0, that's a T. If I have a 1 and a 1 and a 1, that's a G. So this is an example of a tree representation of this prefix code. Let's take another example of a prefix code. So here is an example. A is 00, C is 01, T is 10, G is 11. So this is an example of a prefix code, and the tree representation is like this. All right. So you can see that every prefix code can be written out as a tree. Okay? And the tree has a special structure. So the nodes, internal nodes of the tree don't mean much. The leaves of the tree are where all the action is. I label them with the letters. So every letter lies on the leaf of the tree. Okay? Also, at every internal node, there are exactly two branches. There's a 0 branch and there's a 1 branch. Okay? And sometimes these trees may have nil. So this could be invalid. So you should never see a 111. So that is possible in some trees. even though whenever that happens, you see this is a waste of bits, I might have as well deleted it and put t in here. So typically these trees will never have invalid. Every leaf will be representing a letter. Got it? All right. So this is going to be the tree representation of a prefix code. And these aren't the only prefix code. Let me give you one other example of a prefix code for the same thing. So here I have 5 A, C, T, G. Yeah, let me put the G here. That good? All right. So here in this prefix code, A is the code word 0, C is the code word 100, T is 101, and G is 11. Okay, so here is another example of a prefix code. So you can write down. Let me write it down. So this is another example of a prefix code. As you can see, every prefix code has a tree that's associated with it. And once I have a prefix code, if I take any string, I encode it, then there is only one way to decode it. Okay, so here let me encode A according to this code here. Okay, let me just do that. All right, now how do I decode? Well, decoding is very simple. Let's start at the root of the tree. So if I start at the root of the tree, I encounter a 0. I reach the leaf A. So let me write down A and reset myself to the root. Now I encounter a 1, I encounter a 0, I encounter a 1. Reach a leaf, let me write down the letter at the leaf, go back to the root. I encounter a 1, I encounter a 1. I reach a leaf. I encounter a 0, I reach a leaf. I encounter a 1, I encounter a 0, I encounter a 1. Okay, as you can see, the encoding and decoding are quite painless when you have a prefix tree. All right, now that we have prefix trees, the question is, how do we design an optimal prefix tree? So what does an optimal prefix tree mean? So an optimal prefix tree means that, suppose I have some frequencies. So I know that A occurs 40% of the time. Let's say C occurs 30% of the time, T occurs 5% of the time, and G occurs 25% of the time. Now the question is, if I have a prefix tree like this, then it gives A 1 bit, it gives C 3 bits, it gives T 3 bits, and it gives G 2 bits. Okay, so now the question is, what is the number of bits per character on the average? Well, that's going to be 1 times 0.4 plus 3 times 0.3 plus 3 times 0.05 plus 2 times 0.25. So that gives me 0.4 plus 0.9, 1.3, 1.45, 1.95 bits per character. Whereas if I chose this prefix tree, I can easily calculate and it will come to 2 bits per character. All right. So as you can see, this prefix tree gives me better compression, fewer bits per character on the average than the prefix tree here. All right. So some prefix trees are better than some other prefix trees. So given a set of characters and given the frequencies or the weights for these characters, find a prefix tree that minimizes this number, which is for each character. Let me take the depth. So the depth of A is 1 times the weight for it, which is 0.4. The depth of C is 3, 1, 2, 3 times its weight. The depth of T is 3 times its weight. The depth of G is 0.25 times its weight, which is 2. So take this sum of the weight times the depth. So this is the weight of A times the depth of A in the tree. Okay, so let me take for every character, this is the depth of C times the weight of C. So for every character, let me take its depth times the weight, and that's the average number of bits needed per character. And I want to minimize that number. I want to design a tree to minimize that number. Okay, and such a code is called the optimal prefix code. Okay, now there's an interesting history to it. Claude Shannon, who is the founder of this line of thinking called information theory at MIT, had this open problem in the 50s, and he wanted to find this optimal prefix tree. And this is the classic story that gets repeated again and again in things like Good Will Hunting. Apparently, I mean, this is not quite true. Many people contradict this, but this is the folklore that's come around this, that Claude Shannon had this challenge problem on the board. The student arrives late to class, which is hard to do if you're taking your class remote. But the student arrives late to this class and then thinks it's a homework problem, and it seems to be a tough homework problem. But solves it anyway, and in the end ends up solving an open problem at that time, and thus we get optimal prefix code. I mean, it's apocryphal, it's not quite the right story, but you know, it's somewhat close to the truth somewhere. Okay, so let me just say it out there, and those are called Huffman codes. Huffman codes. Okay, and we will study Huffman codes coming right up on how do you find optimal prefix trees, and the secret is you have to be greedy. But how can you be greedy? In what way will you be greedy? And we will see that in the next lecture. See you then. Bye. Okay, so now we are ready to discuss why are Huffman codes optimal. So why is this greedy algorithm always guaranteed to provide an optimal tree? So let us look at a couple of things that are specific to Huffman codes. So number one thing that's specific to Huffman codes is that if you make a Huffman tree, all right, so you have your alphabet A1, A2, A3, A4, A5, A6, blah, blah, blah. If you take the two least frequent elements in your alphabet, let's call them AI and AJ. So AI has frequency F sub I, AJ has frequency F sub j. If you take the two least frequent, and let's say there are more than two in your alphabet, so let us say alphabet has more than two elements. Let's also say that all elements have different frequencies. Otherwise, we are talking about breaking ties, which let's not worry about that. Let's say everything has different frequencies, so it makes sense for me to now talk about the smallest frequent, the least frequent, and the second least frequent. All right, so the smallest and the second smallest. Makes sense to talk about them. Let's call them A sub I and A sub j. One thing in a Huffman code is that A sub I and A sub j are the nodes with maximal depth in the tree. Okay, so they will be among the deepest nodes in the tree. And number two is they are siblings. And that's always true in a Huffman code. So in the Huffman code, because the very first step in the Huffman code is you're going to take A sub I and A sub j, and you're going to compress them into a composite subtree, right? And when you do that in the Huffman code, you are essentially making them siblings. All right, so if you're agreed about these two facts about Huffman trees, let us talk about why they are optimal. All right, let us say you consulted an expert who's not a believer in Huffman, and the expert said, hey, you know what, I came up with this tree which is better than your Huffman, the tree that Huffman will give you. So the expert came up with a tree, and let's call that tree T star. Why star? Because our expert is a superstar. And so any tree our expert produces has to have a star on it. And our Huffman tree is simply T. I'm going to argue that T and T star, even if they are different, will give you the same value. So I need to argue that the value of t star will equal to the value of t that Huffman produces. Okay? So I'm not going to go through the full proof, I'm going to give you a flavor of the proof. So first of all, I'm going to do a little bit of surgery on this tree. So let's say in t star, you had ai somewhere in the tree and you had aj somewhere in the tree. So first point in t star is that ai and aj must have maximum depth in the tree. So there cannot be any other, let's call ak, a sub k, whose depth is greater, depth of ak is greater than depth of ai, or depth of ak is greater than depth of aj. Let us talk about it. Why is that? So suppose there is an alphabet with a deeper, there is an alphabet, a letter which is deeper than ai or aj in the tree. Okay? So which means that the number of bits used for ai and aj, let's call them d1 bits, di bits and dj bits. Let's say dk was the number of bits used for ak. So I'm saying dk cannot be greater than di or dj. Why is that? If that were the case, then let me take this expert's tree and let me do a switch. So if ai were deeper, let me do a switch between where ak used to be and where ai used to be. Okay, so I'm doing a little bit of a switch in the tree. It's still a valid prefix tree if I did this switch. But what happens to the value of the tree? So value of this new tree, let me call it t sub s, after the surgery, okay, after this surgery, equals the value of the old tree that the expert gave me minus what? So minus the frequency of ai, let me call that f sub I, the depth of ai, d sub I, minus the frequency of ak, depth of ak. So these are the two things I'm removing. I'm switching back and adding. So plus the frequency of ai, but ai is now going to have a depth. So I'm switching it with a sub k, which is deeper, right? So this used to be ai, used to be a sub k, and now they are switching. So minus whatever the frequency of I is, but now this is going to be depth k plus whatever the frequency of k is di. So this is going to be plus fi. So the value of t star plus fi times dk minus di minus fk times dk minus di. But let's say dk was greater than di. So this is a positive number and this is a positive number. All right. And so this is equal to fi minus fk, some algebra, times dk minus di. So this whole thing gets factored out, plus vt star. So this is a negative number, this is a positive number. So therefore, this new tree has a value which is less than the tree of my expert, but my expert is an expert, so this cannot happen. All right. So if the expert is a superstar and I'm so confident of my expert that I'm placing a star on my tree, I shouldn't be able to improve the value of this tree by switching ak and ai. So what does that mean? We are now left with the first conclusion. Okay. So we have our first conclusion that, and similarly for aj. So we have the conclusion that ai and aj must have the maximum depth in the tree. So the maximum depth in the tree, the two least frequent things must have the maximum depth. All right. So which means that if ai and aj were not siblings in my tree, if ai and aj were not siblings, all right, then without any loss of generality, I could, so suppose ai was here, aj was here, and let's say they had some sibling. Okay, I don't care who their siblings are, But if AI and AJ were not siblings, at least they are at the same depth. Okay, they are at the same depth in the tree. We established that. Okay, we established that, and nothing is deeper in the tree. Nothing can be deeper in the tree. So then I can always take A sub j and switch it with whoever AI sibling was, and voila, I have AI and AJ as siblings in the tree. So without any problem, I can switch whoever they are siblings with because they have to have the same depth. All right. Now with that being said, and the value of the tree does not change in this process. So that being said, I have established the first fact, which is that if you have an optimal tree T star, without changing the value of this optimal tree, you can bring the two least frequent elements to the deepest nodes in the tree and make them siblings. Okay, so the two least frequent elements, so this is going to be the deepest part of the tree, or at least as deep as any other part of the tree, and you can make them siblings. Okay, so that brings us one step closer to making this expert tree into my Huffman tree, and showing that while I am making this process of converting my expert tree into my Huffman tree, I am not going to suffer. I am not going to lose the value of the tree, and therefore the Huffman tree is going to have the same value or lower value than the expert tree. Okay, so this is very, very similar to how we proved for the interval. So this is step number one. Step number two is, now that I have done this, let me do the following. Let me take the two characters here, and in fact I could do this to any leaf, but let me take the two deepest leaves, like the two least frequent characters, and let me make it into a composite character with the added frequency of fi plus fj. So let me make a new alphabet set, and let me call this new tree T star and put a hat on it. This hat I'm putting it because I'm taking this tree, taking the two least frequent characters which I have now been able to place side by side, making them into a composite character and making up a new tree. Now if T star was the best possible tree for the original character set A1 through A sub n, then I'm claiming T star hat is the best possible for this new one, which is going to be A1 but AI AJ compressed into a single character AN. So it's the same character set, except that I take AI and AJ, compress them into a single character, frequency F1, Fi plus Fj for this special character Fn. So this new tree must be the best optimal tree for this problem. Why is that? Well, very simple. If there were a better tree for this problem, I could have taken that better tree, and wherever AI AJ existed, I could have just unleashed AI and AJ back into two children, and the value does not change in that process. So if I took this composite character in the tree somewhere, AI AJ, and I unleashed it like this, AI AJ, the value does not change. The value of the tree is still constant. So with that being said, you can now see how I am going to get this interesting process where this T star hat is going to be the same as the original, is going to be the best tree for this composite character. So then what happens? Now I can start doing the whole proof through induction. All right, so I can do the proof through induction. So what is the proof through induction? So the proof through induction is as follows. So I can say, so let me write down my induction hypothesis and show you how the entire induction is carried out, but I'm not going to go through the detailed induction proof, but let me at least walk you through how this induction works. Okay, so the induction statement is going to be as follows. For any alphabet of size n, Huffman tree has least value among all possible trees. Okay, so for any for an alphabet of size n, Huffman tree has the least possible value among all possible trees. Okay, if you want to be more precise, I would say Huffman tree has minimal value among all possible trees. What's the difference between least possible and minimal? Well, least possible usually, often in mathematics, there's the term minimum, which implies that it's the only tree, it's a unique tree with that value. Minimal means that there could be many trees with that value, and Huffman tree is one of the trees that has the least values. All right, so, and we are more implying that if you can find a tree with a small value and you claim that's the smallest, then the Huffman tree can also match or even better your value. That's what we are proving here. And so here is the proof then. Okay, so if that is indeed the case, let us take an alphabet of size n. So base case is alphabet of size 1. So we can prove alphabet of size 1 and even size 2. Because for alphabets of size 1 and 2, there's just one possible prefix tree, and that is the same prefix tree that Huffman will produce, and that's optimal. So for 1 and 2, it's easy. Now, induction hypothesis is if this is true for a tree of size n, then it has to be true for a tree of size n plus 1. And that's where this argument fits in. So if it is true for take any tree of size n plus 1. So if it is true for a t of size n plus 1, and you say it's an optimal tree t star for an alphabet of size n plus 1, then what you can prove is in t star, ai and aj, without loss of generality, ai and aj can be made siblings in this tree. And then they can be compressed to produce a new tree t star hat, which is going to have ai and aj as a composite alphabet. And now you apply this alphabet has size n, so now the induction argument applies. So there is a Huffman tree t hat that Huffman code will produce on this. And if you take the tree that Huffman code produces on t hat and then expand ai and aj out, that's the code that Huffman will produce on the entire alphabet A1 without AI and AJ combined. So that's how you carry through an induction argument to show that Huffman is going to give you the minimal value among all possible trees for a given alphabet size. All right, so I went through this rather fast, but the book has this entire argument explained rather nicely, so I hope you will have the time to go through this argument and see how it works and compare it with the argument we made for the interval scheduling. And in each of these cases, you see how we are going through. We assume someone expert is coming up with the best solution, and then we take that best solution and we show without loss of generality, our greedy algorithm, our greedy choice could be substituted in somehow, and somehow we can take that best solution and even morph it into a greedy solution without losing in value. And by doing so, we show that the greedy solution is better or as good as any other solution you can come up with. This is typically how it works. There is a very beautiful general theory underlying this. It's called the theory of greedy matroids. If you're interested, it's also covered in the book, but it's an advanced topic. Would not advise you to go over it just now, but it's a very interesting topic on when greedy algorithms can be formulated to work optimally for a problem. All right, so that's mostly all about greedy. Hopefully this was entertaining and fun. Okay, so now we are going to look at optimal prefix codes. So optimal prefix codes. We already saw what a prefix code was, right? So suppose you're given a set of letters, right? So in our favorite sequence of letters, the letters that make up all life on Earth, A, C, T, and G. So let's take DNA strings, all right? And let's say A occurred, let's say 40% of the time, T occurred 40%, whereas C and G occurred just 5% of the time. Does that add up to 1? No. So to add up to 1, let's make C and G occur 10% of the time. All right. Okay. So here we go. So this is the frequency, let's say, or the fraction of time that you get A, C, T, and G for a really long DNA string. All right, so this is the frequency. And we also would like to have a prefix code. And we saw that prefix codes are represented by trees. So here is an example. So here's an example of a prefix code that's representing a tree. Here A is represented by the code word 0, 0, C by 0, 1, T by 1, 0, G by 1, 1. All right, and every letter has a depth, is a leaf in the tree and has a depth. So depth of A equals 2, depth of C equals 2, depth of T equals 2. Depth is also the same as the number of bits that you are using to represent that letter, equals 2. And this prefix tree has a value. The value of this prefix tree is summation over all the alphabets. Let me call my alphabet set sigma. In this case, sigma is A, C, T, and G, 4 letters. It's the summation over all the alphabets in sigma, the frequency of that alphabet times the depth of the alphabet is going to be the value of a given tree. So what's the value of this tree that I have given? So it's the summation over the alphabet f of A, D of A, that's going to be 2 times, which is the depth of A times the frequency, 0.4, plus 2 times 0.1, plus 2 times 0.4, plus 2 times 0.1, and this is just 2. So, and this value is the average number of bits per character in our code. Okay, and we want to minimize this value. So what are Huffman codes? Well, Huffman codes are find a prefix tree, find a prefix code, or a tree. Okay, same thing, a very special kind of a tree like this, such that the value of the tree is minimized. All right, so this is the overall problem for finding a Huffman code. All right, so how do we do it? So here is the basic idea. So Huffman code is basically obtained through a greedy algorithm. So let me explain this greedy algorithm and then convince you that this greedy algorithm gives me the best prefix tree over all possible trees that you can imagine involving, in this case, the 4 characters, but this works for anything. All right, what's the idea here? So let me explain on this character set. So first step is take the 2 least frequent characters. Okay, and if there are ties, then you break ties arbitrarily. So if there are multiple characters at the same frequency, break it arbitrarily, but take the 2 least frequent. So in this case, we will have C and G are the 2 least frequent, and they are 0.1. All right. So next step is form a composite, and this is kind of interesting, character by combining them. Okay, so form a composite character by combining them. So what is that? So in this case, I'm going to make a new character, and this character is going to be a little treelet. Okay, so it's going to be, let me call it a treelet, even though you won't find this term anywhere. So it's going to be a little treelet which says, if it's a 0, give me a C, if it's a 1, give me a G, and it has a combined frequency of 0.1 plus 0.1, 0.2. So now I have A with 0.4, I have T with 0.4, and I have this combined character CG with 0.2. Okay, so think of this as a new problem again and run the same algorithm on this new problem. So when I run the same algorithm, let me take the 2 characters that are least frequent in this new set. So here the 2 new, in this new set, T and this composite character CG are going to be the 2 least frequent. So T and CG. So let me write CG in this bracketed format and form a composite character by combining them. So now I'm going to combine T with CG. Now what does that give me? That gives me a new treelet. Okay. So in this treelet, what am I going to do? On a 0, I'm going to go to T. On a 1, I'm going to go to CG. But CG itself is a treelet, so let me expand it here. Okay, you see where I'm going with this? 0 on a 1, CG. So this is my new treelet. It's actually a subtree. That's the right name for it. I shouldn't be calling it a treelet. I should be calling it a subtree. Okay, it's a subtree that I'm creating by combining T and C and G. So what frequency do I associate to this? To this, I associate a frequency 0.6. So now I'm going to greedily combine these two, and I get a new tree. Okay, with frequency 0.6. Last step, take the two least frequent characters. Now that's going to be A and T, C, G. Okay. With A and T, C, G, you see how this bracket representation nicely represents the whole subtree in a nice linear fashion. Okay. All right. So now what? So now I'm going to combine those two because those are the two least frequent. Combine them into a full. So now I'm going to get 0 as an A. On a 1, I'm going to get T, C, G. But expand that subtree out. What do you get? You get, again, on a 0, a T, on a 1, on a 0, C, and a G. And this is going to have a frequency of 1. And then we are done. And then we are done because we have taken all the characters in our alphabet and we have combined them and we are done. All right, so now it's going to be 1, 0, A, done. Okay, so this is the final code. And this is it. All right, so it's a greedy algorithm. What's a greedy algorithm? At any point, take the two least frequent, not the most frequent, the least frequent, and combine them into a composite character. If they're already composite characters, then you're combining the subtrees into a new subtree and give it a frequency which is the sum of the frequency of the two characters I'm combining. Keep doing this until the entire alphabet has been coalesced into a tree. And here's what we get as our final code. Okay, and what's the value of this code? Okay, so A is 0.4 times the depth of A is 1 plus T has a value of 0.4 times the depth of T, which is 2, 1. C and G have a depth 3, so 0.1 times 3 plus 0.1 times 3. And what's the answer? 0.3 plus 0.3, 0.6 plus 0.8, 1.4, 1.8. So now I get a value of 1.8 bits per character. Whereas originally my code had a value of 2 bits per character, my new code has 1.8 bits. Can we read it off as a code? Yes. The new code is going to be assign A the code string 0, T the code string 10, C the code string 110, and G the code string 111. Okay, and this is the prefix code we derive, and this is going to be the optimal prefix code. All right. Now let's generalize this beyond this example, but the generalization is very, very simple. This is it. Take the two least frequent characters, form a composite character, and repeat until just one big composite character remains. That's it, and that forms your tree. So hopefully you can see how this procedure works and how to work it by the hand. Coming up, we are going to argue why is this the most optimal among all possible trees that could be imagined. All right, see you soon. Okay, so now we are going to look at optimal prefix codes. So optimal prefix codes. We already saw what a prefix code was, right? So suppose you are given a set of letters, right? So in our favorite sequence of letters, the letters that make up all life on Earth, A, C, T, and G. So let's take DNA strings, all right? And let's say A occurred, let's say 40% of the time, T occurred 40%, whereas C and G occurred just 5% of the time. Does that add up to 1? No. So to add up to 1, let's make C and G occur 10% of the time. All right. Okay. So here we go. So this is the frequency, let's say, or the fraction of time that you get A, C, T, and G for a really long DNA string. All right. So this is the frequency, and we also would like to have a prefix code, and we saw that prefix codes are represented by trees. So here is an example. So here is an example of a prefix code that's representing a tree. Here A is represented by the code word 0, 0, C by 0, 1, T by 1, 0, G by 1, 1. All right, and every letter has a depth, is a leaf in the tree, and has a depth. So depth of A equals 2, depth of C equals 2, depth of T equals 2. Depth is also the same as the number of bits that you are using to represent that letter, equals 2. And this prefix tree has a value. The value of this prefix tree is summation over all the alphabets. Let me call my alphabet set sigma. In this case, sigma is A, C, T, and G, 4 letters. It's the summation over all the alphabets in sigma, the frequency of that alphabet times the depth of the alphabet is going to be the value of a given tree. So what's the value of this tree that I have given? So it's the summation over the alphabet F of A, D of A, that's going to be 2 times, which is the depth of A times the frequency 0.4 plus 2 times 0.1 plus 2 times 0.4 plus 2 times 0.1, and this is just 2. So, and this value is the average number of bits per character in our code. Okay, and we want to minimize this value. So what are Huffman codes? Well, Huffman codes are find a prefix tree, find a prefix code, or a tree. Okay, same thing, a very special kind of a tree like this, such that the value of the tree is minimized. All right, so this is the overall problem for finding a Huffman code. All right, so how do we do it? So here is the basic idea. So Huffman code is basically obtained through a greedy algorithm. So let me explain this greedy algorithm and then convince you that this greedy algorithm gives me the best prefix tree over all possible trees that you can imagine involving, in this case, the 4 characters, but this works for anything. All right, what's the idea here? So let me explain on this character set. So first step is take the 2 least frequent characters. Okay, and if there are ties, then you break ties arbitrarily. So if there are multiple characters at the same frequency, break it arbitrarily, but take the 2 least frequent. So in this case, we will have C and G are the 2 least frequent, and they are 0.1. All right. So next step is form a composite, and this is kind of interesting, character by combining them. Okay, so form a composite character by combining them. So what is that? So in this case, I'm going to make a new character, and this character is going to be a little treelet. Okay, so it's going to be, let me call it a treelet, even though you won't find this term anywhere. So it's going to be a little treelet which says, if it's a 0, give me a C, if it's a 1, give me a G, and it has a combined frequency of 0.1 plus 0.1, 0.2. So now I have A with 0.4, I have T with 0.4, and I have this combined character CG with 0.2. Okay, so think of this as a new problem again and run the same algorithm on this new problem. So when I run the same algorithm, let me take the two characters that are least frequent in this new set. So here the two new, in this new set, T and this composite character CG are going to be the two least frequent. So T and CG. So let me write CG in this bracketed format and form a composite character by combining them. So now I'm going to combine T with CG. Now what does that give me? That gives me a new treelet. Okay, so in this treelet, what am I going to do? On a 0, I'm going to go to T. On a 1, I'm going to go to CG. But CG itself is a treelet, so let me expand it here. Okay, you see where I'm going with this? 0 on a 1, CG. So this is my new treelet. It's actually a subtree. That's the right name for it. I shouldn't be calling it a treelet. I should be calling it a subtree. Okay, it's a subtree that I'm creating by combining T and C and G. So what frequency do I associate to this? To this I associate a frequency 0.6. So now I'm going to greedily combine these two, and I get a new tree. Okay, with frequency 0.6. Last step, take the two least frequent characters. Now that's going to be A and T, C, G. Okay, with A and T, C, G, you see how this bracket representation nicely represents the whole subtree in a nice linear fashion. Okay, all right. So now what? So now I'm going to combine those two, because those are the two least frequent, combine them into a full. So now I'm going to get 0 as an A. On a 1, I'm going to get T, C, G. But expand that subtree out. What do you get? You get, again, on a 0, a T, on a 1, on a 0, C, and a G. And this is going to have a frequency of 1. And then we are done. And then we are done because we have taken all the characters in our alphabet and we have combined them, and we are done. All right, so now it's going to be 1, 0, A, done. Okay, so this is the final code. And this is it. All right, so it's a greedy algorithm. What's a greedy algorithm? At any point, take the two least frequent, not the most frequent, the least frequent, and combine them into a composite character. If they're already composite characters, then you're combining the subtrees into a new subtree and give it a frequency which is the sum of the frequency of the two characters I'm combining. Keep doing this until the entire alphabet has been coalesced into a tree. And here's what we get as our final code. Okay, and what's the value of this code? Okay, so A is 0.4, times the depth of A is 1 plus T has a value of 0.4 times the depth of T, which is 2, 1. C and G have a depth 3, so 0.1 times 3 plus 0.1 times 3. And what's the answer? 0.3 plus 0.3, 0.6 plus 0.8, 1.4, 1.8. So now I get a value of 1.8 bits per character. Whereas originally my code had a value of 2 bits per character, my new code has 1.8 bits. Can we read it off as a code? Yes. The new code is going to be assign A the code string 0, T the code string 10, C the code string 110, and G the code string 111. Okay, and this is the prefix code we derive, and this is going to be the optimal prefix code. All right. Now let's generalize this beyond this example, but the generalization is very, very simple. This is it. Take the 2 least frequent characters, form a composite character, and repeat until just one big composite character remains. That's it, and that forms your tree. So hopefully you can see how this procedure works and how to work it by the hand. Coming up, we are going to argue why is this the most optimal among all possible trees that could be imagined. All right, see you soon. Okay, so now we are going to look at the final topic in our course, and which is going to be the topic that concerns the study of decision problems, languages, and complexity classes. So this is by the way of introduction to a broad field of study called the theory of computation, okay, and which is very closely related to algorithms, okay, and this studies the inherent difficulty of solving problems, okay, inherent difficulty of solving problems. So what you will learn from this is certain problems are inherently hard, and we know why. Certain problems are inherently easy to solve on a modern computer, and certain problems we do not know. We do not know whether these problems are inherently difficult or it's the lack of human ingenuity and imagination that prevents us from finding good solutions. So in this lecture, I'm going to lay some foundations for thinking about problems, the concept of decision problems, languages, and introduce the notion of complexity classes, culminating with looking at 2 very important complexity classes, P and NP, and I will explain what these are in the course of this lecture. Okay, so throughout this course, we have studied algorithms for problems. So we have studied algorithms to solve problems, okay? And somehow we've never formally defined the notion of what a problem means, okay? And we are going to try and do that, try and capture this notion of what is a problem, all right? So let's take an example of an algorithm. So we are given an array A of n elements, and we are asked, does element E belong to the array A? Okay, and so we are designing a box, and let's call this problem belongs to array problem. So we are interested in a box belongs to array. Okay, so that's the name of the box. In goes in an array A, in goes in an element E, and out comes an answer yes or no. Yes if E belongs to A, no if E does not belong to A. And an algorithm is used to fill this box in. So an algorithm is a procedural way of implementing this box, all right? And such a box which has a yes-no answer is called a decision problem. It's a problem whose answer is always always yes or no. As an example, let's take examples of decision problems. So given a graph G and two vertices S and T, which belongs to the graph, does there exist a path from S to T? Let's call this the path exists problem. And this is an example of a problem with a yes-no answer. Okay, so here we are given a graph, we are given two vertices in the graph, and we want to know yes if S is connected to T, no if S is not connected to T. Okay, so this is an example of another decision problem. Let me give you one more decision problem. So for example, given a number, we can ask if the number is prime. So given a number, and typically you have to write down the number in a binary representation of the number. Given a number n in binary, okay, as an example, I gave you an example, is n prime? Okay, so this is an example that takes in an input, a number n, encoded in binary, yes if it's prime, no if it's not prime. Alright, so decision problems are problems with yes no answer. But then the question is, are all problems decision problems? Clearly not. What are examples of problems that are not decision problems? Well, for example, sorting is not a decision problem. Given an array A, your goal is to find a sorted array A. So that's clearly not a decision problem. Okay. Now, what are the other examples of not a decision problem? We looked at knapsack. Okay. If you take knapsack, you have a bunch of items whose weights are known, whose value is known. Okay. You have a weight limit W. Then the question is, choose items of maximum value such that total weight is less than equal to W. Alright, so this is another example of something that's not a decision problem. The answer is not yes or no. The answer is a list of items. So if you have knapsack, you have a list of items, you have their value, then the answer is a subset of items maybe that maximizes the value such that, oh, by the way, you have to give me the weight limit, capital W. The answer is a subset of items. Okay, so these are examples of clearly not decision problems. What about another example of something that is not a decision problem? Let's say factoring a number. So in factoring a number, you're given a number n and you're asked to give me the smallest factor, let's say p of n. So you're given a number n, which is the, let's say, even the product of two prime factors pq, and you want to give the smaller of the two prime factors. That's the result. So this is called factor. So here the result is not a decision problem. Okay, so many problems are clearly not decision problems, but you can make, for many problems, you can have a decision version of the problem. What does it mean to have a decision version? Let's take an example. Let's start with factoring a number. Okay, so instead of calling factor, let me call a new decision version, factor. Okay, let me put a question mark. Let me give you a number n to factor, and let me give you an index I, and I'm asking the question, okay, so I'm to frame everything as a question, is the ith bit of the smallest factor p 1. Okay, and this is, let's call this the decision version. Instead of saying that, let's given a number n, let's say 35, which is 7 cross 5. So I'm asking, give me a number n equals 35, give me a bit index I, let's say 2. I'm asking, is the second bit of the smaller factor a 1? Okay, so if I ask this kind of question, I've changed the problem, but interestingly enough, if I can solve the decision problem, I can use it as a subroutine to quickly extract the factor. Do you think that's possible? Can I use the decision version? So if I gave you the number n and I gave you the index I, and I can tell you whether that index is a 1 or a 0, do you think you can quickly figure out, by repeatedly calling the decision version, can you quickly figure out the factor? Yes, of course. All you need to do is start from I equals 1, I equals 0 to I equals log n, okay, and in fact half log n really. So this is going to be the number of bits of p will have to be less than equal to the number of bits of n divided by 2. Okay, so p cannot have more than half the number of bits of n. Okay, so therefore, if number of bits of n is roughly log n, so I going from 0 to log n, repeatedly run this, and you can get the answer. So you can extract the factor. So what about the knapsack problem? Recall the original knapsack problem gave you a list of items, gave you a total weight, and asked you to find a selection of maximum value. So find a selection. So here the idea was, in the knapsack, find a selection of maximum value. Okay, instead of that, the decision version will become, is there a selection of value greater than or equal to some value limit v? So instead of saying find a selection of maximum value, say, is there a selection of value greater than equal to v? If I know that the answer for this, I can use binary search to actually narrow down on the maximum value selection. Okay, so all I need to do is, instead of answering this question, find the selection of maximum value, I can instead ask the decision version, which always has a yes and no answer. Is there a selection of value that's at least capital V? Just like I gave a capital W limit on the total weight, let me ask, is there at least capital V that I can get? What about sorting? It's a little bit lame, but I can always ask the decision problem, is element E the ith element in the sorted array A? Okay, so this is not very convincing. Sorting does not have a good decision version. Okay, so not all problems have a nice decision version, but I claim that most problems that we are interested in have a nice decision version. Okay, So most of what we are going to be concerned with in this lecture are going to be decision problems, problems with yes, no answer. So decision problems. Why are decision problems nicer to study? Well, there are two answers to it. Number one is the size of the answer is just 1 bit. So things like computing a big answer. So suppose you had one problem where the answer was very big and another problem where the size of the answer was very small. Then comparing them in terms of the size of the inputs is not that useful, because the size of the answer is going to matter. So for example, problems like compute the first 1,000 digits of pi, 10,000 digits of pi, are not problems for which we care to analyze the complexity. So we want to standardize the size of the answer, and the easiest standardization is to have a 1-bit answer, a yes or no, and that's just 1 bit that comes out of the problem. Okay, so that is one way of thinking about it. It makes for a useful way of thinking about problems. All right. The second useful thing is that we can make a connection between problems and languages. Okay, and unfortunately I'm not going to have a lot of time in this class to make this connection. This is typically a connection that's made in a proper theory of computation class. Okay, and if you ever get to take one, I highly recommend. These connections are made, but it's an optional class. It's typically a theoretical class, a mathematical class, okay, and that's kind of optional. So we will make this connection in terms of languages, but let me just explain very quickly. All right, so whenever you have a decision problem, you define a set of all. So decision problem has two answers, yes or no. Define set of all inputs which gives us the yes answer, and we call this the language, okay, associated with the problem. Why is it called a language? It's called a language because this set is going to be a set of all encodings. So let me give you an example. Let us take the language prime equals the set of all binary numbers n such that n is a prime number. So this language is going to have what? 1 0 1 1, okay, 1 0 1. So this is just 2 3 5 1 1 1 7 and so on. All right, so this is going to be the language. All right, so this language can be thought of as a subset of binary strings made of zeros and ones. Okay, now let us call the path language, and this is a slightly more difficult language. It's a set of all graphs with source node, destination node, such that G encodes a graph, S is a node in the graph, T is a node in the graph, and S is connected to T in the graph. So this is the language of all graphs which are connected to paths. And once again, we encode it as a binary string. Okay, we encode all this information as a binary string. All right, so there is going to be a way in which I view all problems as in terms of the sets of inputs which gives us the yes or answer, and this is called the language associated with the problem. Okay, so this is using this notion of language, we can start to standardize a lot of what we mean by a problem. Okay, so how do you define a problem? Well, a problem is defined by a language. A language is defined by choosing certain strings, okay, which have some meaning. This has some meaning, but I don't have to really tell you what the meaning is. So this could be an encoding of a number, encoding of a graph, and so on. Okay, so these are called languages. All right, and starting from the early 20th century, people started studying languages in terms of their how do you build algorithms. So an algorithm is now can be formally defined as a box, okay, as a box which, given an input string, okay, tells me if X belongs to a language, so L. So this algorithm, this is called algorithm that recognizes language L. Okay, now what kind of a machine runs this algorithm, right? That is very, very important. And I'm going to skip through a ton of details and just tell you that there is a very universal class of machines called Turing machines. Okay, now what's a Turing machine? So a Turing machine, which was, by the way, invented by the scientist Alan Turing, very, very fascinating person who is very rightly called the father of modern computer science. All right, and Alan Turing came up with this model of a computer. Okay, and in Turing's model of a computer, there is basically some kind of a logic. Okay, I'm not going to describe it too much, which is going to read from a tape. Okay, and on this tape is written a string. All right, and it's going to at some point either say yes or no. So it's going to stop at some point and say yes or no. And when it reads a character in the string, it can move the tape head either to the left or to the right and internally shift to a new state. Okay, I am glossing over a lot of details here just to get you on the same page in terms of what's the model of a computer. Okay, and it turns out that this very, very simple model of a computer, and what does this logic look like? This logic looks like this. This logic looks like this. So you have some states as 0. If you read the string 1, you could go into state 1, and then you tell the machine to move left. If I read a string 0, maybe I stay in state 0, tell the head to move right. And then certain states are stop states. So you can have stop states, stop and accept and say yes. Certain states you can stop and say no. Okay, so this is how the logic is built. All right, and each arrow says, if I am in S1 and I read a 0 on the tape, then let me move right and move to S2. If I am in S2 and I read a 0 on tape, let me move left and stay there. If I am in S2 and I read a 1, let me move right. So these are going to be kind of the transitions. So these are going to be the transitions. All right, and this is a very, very simple model of a computer. Okay, this is a super simple model of a computer. But interestingly enough, everything that our machines can do, our RAM-based computers can do, can be captured by a Turing machine. And likewise, everything that's captured by a Turing machine can be captured by the RAM-based computing model that we are used to. Likewise, it turns out that any physically realizable model, so people came up with lots of physical models of computation. So they came up with RAM-based machines, the kind that runs our programs these days. Well, those were shown to be equivalent to a Turing machine in terms of computing power. They came up with something called lambda calculus, which influences the design of lots of programming languages, and this was by someone called Alonzo Church, and that was shown to be equivalent to a Turing machine. Something called a post machine, and that was shown to be equivalent to a Turing machine. Marvin Minsky, a very famous computer scientist, came up with something called a Minsky machine. That was turned to be equivalent to a Turing machine. Quantum computers, which we will briefly look at next week, were turned out to be equivalent to a Turing machine. So it turns out that there is a thesis which is fundamental to computer science, and this is called the Church-Turing thesis. And it says that Turing machines are a universal model of computation, which means that anything that we can compute using a physical device, any physical device that can carry out any form of computation, it's taken to be equivalent to a Turing machine. In other words, this is a thesis. This is not a theorem. This is just saying that it's an article of belief, and we believe firmly, due to lack of evidence to the contrary, we believe in this thesis. And this thesis says that any physically realizable computing device is equivalent in its computing power in terms of what it can compute to the model of computation that Turing proposed, that's called a Turing machine. Okay, and this is central to computing. So what it means is that Turing machines came out as a model of computation. Now if you go back to all the boxes that we wrote down, prime, path connected in a graph, kth bit of factor, all the decision problems we wrote down, what we are looking for is an algorithm, okay? And algorithms are meant to be run on Turing machines. And obviously in this course, we don't teach you algorithms on Turing machines because they are completely impractical to write Turing machines. But we taught you a lot of algorithms using pseudocode that was supposed to run on these RAM-based machines. And that was for a reason, because these RAM-based machines have been shown to be equivalent to Turing machines separately, and so we never have to worry about whether our pseudocode is physically realizable, because we know it is physically realizable, because it can be realized on a RAM-based machine, and the RAM-based machine is equivalent to a Turing machine. Okay, and we did not define these things because it gets a little bit tedious at this stage of your education. All right, so what am I getting to? What I'm getting to is there is a first boundary between problems that can be solved on a computer, on any computer as we believe computers are defined. So on any computer, problems that can be solved. And outside this are problems that cannot be solved on a computer. So we get to our first shocking realization. Not everything that we care about has an algorithm. So there are certain problems outside. There are, of course, many problems here that have an algorithm. Everything we've studied in this class belongs to inside this box. Example, problems that can be solved using a DFS, whether there exists a cycle in a graph, whether a number is a prime number, the kth bit of the factor, the decision version of knapsack. So we have seen plenty of problems inside this box. But interestingly enough, there are problems that lie outside this red box that cannot be solved on a computer. Okay? And these kinds of problems have a name. They are called undecidable problems. And likewise, problems that are inside are called decidable problems. Okay, so there is decidable problems in this world and there are undecidable problems. Undecidable problem means that no Turing machine can solve this problem. And therefore, by equivalence of Turing machine, RAM machines, and so on, the computers that we have today, that we are physically capable of constructing, cannot solve these problems. So what are examples of undecidable problems? Examples of undecidable problems. Okay, there are plenty of examples of problem. The first example that Turing put forth is known as the halting problem. So let us say I give you a program, okay, as an input, and I want you to build a smart IDE that says, does this program have an infinite loop or not? No, if program does not have infinite loop. Okay, so this is called the halting problem. So I want to build a smart compiler. I want to build a smart compiler that solves the halting problem. What is the halting problem? It says that given a program, so suppose I give you the file, the text file of the program we wrote. Let's say the program you wrote for your programming assignment, dfs.py. So given a Python program, I want to give this compiler to take in this Python program and say yes if the Python program has an infinite loop, no if it does not have an infinite loop. And this is called the halting problem. Turns out you cannot solve the halting problem. There is no algorithm is capable solving this problem. Which is very, very, very surprising, but it is a very, very powerful result. You cannot solve this problem. Now, what about problems of the kind we could care about that are undecidable? There are examples. For example, the Diophantine equation problem, also known as Hilbert's 10th problem. Okay. Now suppose I have a polynomial equation. Let's say x squared minus y squared equals, I don't know, 5. Okay. So I want to know, are there two squares whose difference is 5? And x and y are integers. Okay. Does this have a root? Does this have a solution? Does this have an integer solution? So suppose I'm given a polynomial, what's called a Diophantine polynomial, which means the coefficients are all integers. The coefficients are 1 times x minus 1 times y squared equals 5. Suppose I'm given such a polynomial. Does it have a solution where x and y are integers? And yes, in this case, the answer is yes, it does have a solution. And if you take x equals, I don't know, 3 and y equals 2, you see 3 squared minus 2 squared is 5. Okay, so it does have a solution. Now, what about, for an example, what about an equation like this? X cubed plus y cubed plus equals z cubed. Does it have a solution? It does. The answer is x equals 0, y equals 0, z equals 0. So that, for example, it does have a solution like that. All right. But you can ask more interesting questions of the same form. So you're given a polynomial, x, y, z, multivariate polynomial. Okay. And you want to ask, is there an integer? Okay, so you're given an equation. I want p to be equal to 0. Is there integer assignments to the variables that makes p equals 0? And the answer is, it's called the Diophantine problem. And in 1900, around the turn of the century, David Hilbert posed this as one of the questions that's going to keep mathematicians busy over the 20th century. And he was right. Around the 1970s, Yuri Matiasevich, I can't say which, I really am bad at writing Russian names, with earlier contributions from Martin Davis and Julia Robinson. Okay, so with earlier contributions from Davis and Robinson, he found out a proof that this is undecidable, which means that there is no way to find, given a general polynomial, there is no algorithm that will work through the polynomial and decide whether there are integer assignments that can make the polynomial 0 or no such assignments exist. Okay, so these are examples of problems that you cannot solve by computers. So these are unsolvable problems. Okay, so we've already made our first distinction. We cut the world of problems into problems that are decidable, which means they can be solved in the first place by a computer, and undecidable, which means these are problems that cannot be solved by a computer no matter what. Okay, because no physical model of computation is capable, no currently known physical model of computation is capable of solving these problems. Now, even in decidable, not every problem is of interest to us. We want to know what are decidable problems that can be solved fast and problems that cannot be solved fast. Which means not only am I interested in knowing that there exists an algorithm, I want to know there is a fast algorithm that can solve it for large inputs in no time, within the blink of an eye. Right? So I'm really interested in knowing the answer between what can be solved fast and what cannot be solved fast. Are there fundamental limitations in the world, in mathematics, in computing, in physics, that make it difficult for us to solve certain problems rapidly? Okay? And this is going to be the topic of the very next lecture, where we are going to talk about the complexity classes between polynomial and exponential time, which separates the notion of a fast algorithm and a slow algorithm. And that's coming up in the very next lecture. See you then. Bye. Okay, so in the previous lecture, we looked at a dichotomy where we classified problems, okay, as decidable and undecidable. Okay, problems that can be solved with a computer in the first place and problems that cannot be solved. And we even looked at a couple of examples like the halting problem, like the Diophantine problem, and so on, Hilbert's 10th problem, and so on. All right. Now, we further said that it's not enough that it can be solved by a computer. We wanted problems that can be solved fast by a computer, and we wanted to look at problems that may be not so fast. Okay. But what does fast mean? So what does fast mean? So this needs a definition. What do we mean is fast? Well, if on input of size n, if we get an algorithm that runs in theta log n, we accept that it is fast. If we get an algorithm that runs in theta n, we accept it's fast. It's a linear time algorithm. If we find an algorithm that runs in theta n squared, maybe it's fast. I don't know. So it all depends, right? If you find an algorithm that runs in theta 2 to the n, usually you say it's slow. All right. So often fast means that large inputs can be solved, and I'll put large within quotes, in reasonable, again within quotes, time. Okay, so this requires some form of consensus. So it's not like a mathematical thing. We need to agree what is fast. Okay, and one of the areas of, and this is kind of slightly controversial, but the line is drawn between algorithms that run in polynomial time, in size of input, versus algorithms that do not run in polynomial time. Okay. Now, what are examples of algorithms run in polynomial time in the size of the input? As an example, let us take an algorithm that given a graph, given two vertices S and T, decide if there is a path from S to T. Well, this algorithm can be solved in linear time in the size of the graph by simply running a DFS starting from S. And if you hit T in the process of doing the DFS, then voila, you found a path. If you cannot hit T, then of course there is no path from S to T. So this kind of an algorithm is polynomial time, because if the size of the graph is the number of vertices plus number of edges, if this is n, this runs in time that's linear. Okay, let's take another example. Let us say I am given two numbers, n1, okay, and n2 of size k1 bits and k2 bits, and I need to find out some, I multiply them, and I want to find out the ith bit of the result. Okay, to make it like a yes/no problem, I want to ask whether the ith bit of the result is 1. Okay, after multiplying these two numbers. Well, we already studied fast algorithms for multiplying, like the Karatsuba algorithm, and for two n-bit numbers, okay, let's take the size to be the maximum of the two numbers. Then Karatsuba runs in n to the power 1.54, blah, blah, blah. We already studied this, and this is also a polynomial time algorithm. In fact, if polynomial was all we interested in, we could have run grade school in time n squared. So these are examples of algorithms that can be run in polynomial time. And we say these algorithms are fast. So that we make a mapping between things that run in polynomial time in the size of input, okay, and we claim that's fast. Now, what about an algorithm like factoring? So given a number n, which we know secretly can be factored as p times q, I want to recover the smaller of the two factors. And I already showed you how to make it into a decision version in the previous lecture. So let us assume it's actually a decision version. All right. The question is, how fast is it in the size of the input? Well, if you did a brute force search for factor, that runs in time which is proportional to square root of n. And this was the programming assignment in CSCI 2824 for some of us, right? So we saw this algorithm, and this algorithm is not fast. Why is that? Because the input size for a number n in binary is k equals log n. Okay, and therefore square root of n is nothing but 2 to the power k over 2. Okay, so therefore if k is the size of input, the algorithm runs inside 2 to the power k over 2. And we saw this effect when we increased the number from k equals 20 bits to k equals 22 bits, for example. You saw how much the time to factor went up. So the time to factor rose by a factor of 2 roughly. So if this took about 10 seconds to factor, then this took about 20 seconds to factor. Right? So every 2 bits you add doubles the time that you need to factor, and that's not practical. If you want to factor a 1000-bit number, forget it, right? It's not going to be easy, and we already noticed this. So this was clearly seen. Okay, so this was clear from what we looked at previously. So even though it's controversial, lots of computer scientists have made the firm determination that something that runs in polynomial time can be considered to be fast. Okay, now this requires a little bit of explanation. Why is this the case? Well, if you have an algorithm that runs in time theta n to the power 100, it's not going to be fast even for small n. This is going to be slow. But on the other hand, what we find is that this kind of an algorithm is more or less unknown. Most algorithms that are polynomial time that we know of do have very, very small indices like n squared, n log n, n to the power 1.54, blah, blah, blah. So most algorithms that we know of have exponents that are relatively small, like 1, 2, or 3. A vast majority of algorithms, useful algorithms, have small exponents. So this means that it really makes things in favor of saying that polynomial time algorithms are somehow delineating the boundary between what is fast and what is not fast. Okay, so having said this, there is a different class of algorithms. So polynomial time is the class of all problems that have an algorithm running in big O n to the power c for constant c. So for example, if you have theta n log n algorithm, that's big O n squared, so you have n to the power c for a constant c. So having this n to the power c for a constant c and using big O instead of big theta allows us to do upper bounds, but it's okay. And it allows us to include things that are not polynomial like n log n. Alright, so polynomial time. Alright, so now we have a further refinement. So here is the class of all decidable problems, problems that can be solved in the first place. And inside this is a class of all polynomial time problems. Alright, and interestingly, there are problems that are known to be non-polynomial time. Like exponential time problems. So there are problems which are known to be hard exponential time. Okay, exponential time problems. Okay. Okay, so are there problems that are known to be in exponential time? Yes, there are problems that are known to be in exponential time, which means that we know that there cannot be any polynomial time algorithms, but let us not worry too much. I can post some examples on Piazza. The thing that I'm afraid of is many of you may not recognize immediately what these problems are or what they mean, but I can always post some examples on Piazza. But the main point is, we know that certain problems are definitely not in polynomial time. They cannot be solved. We know certain problems are definitely in polynomial time. How do we know that? Because we actually know algorithms for this problem that run in polynomial time. What are examples? So examples are, let's say, given a graph, does it have a cycle? How do we solve it? Well, you do DFS and check for back edge. So this is definitely theta b plus e. Okay, as an example, another famous recent example, given a number n, is n prime. Okay, so given a number n is n prime. This was not known to be polynomial time, but recently, well, recently means about 15 years ago, there was a paper by Agarwal, Kayal and Saxena that proved that this can be solved in polynomial time. Note that this is different from the factoring problem. This is different from factoring problem. In factoring problem, you're given a number n, which is known to have factors p, q, let's say. And then you're asking things about the, let's say, the smaller factor pq. So this is different from the factoring problem. Here, you're just given a number n and you're asking if it's prime or not. Not prime. You're not asking anything about the factor. So all you're asking is there a factor or is there not a factor? That is different from saying, can you tell me something about the factor? Right? So it's almost like saying, is it an elephant? Is it not an elephant? Sure. Now, if it's an elephant, can you tell me more about the elephant structure? Well, more about the elephant structure is hard, but telling whether it's an elephant or not an elephant is easy. Okay, and where elephant means it's a prime. Okay, so here these are examples of problems that can be solved in polynomial time. Okay, and we've seen lots of examples in our class. Given an array is its median less than equal to 0. So is the median of an array of numbers less than equal to 0? That's an example of a polynomial time, because you can always find the actual median in theta n time, and you can use that to decide if the median is less than 0 or greater than 0. All right. So these are examples of polynomial time algorithms. Okay. Now, there are some algorithms which are called NP, standing for non-deterministic polynomial time. What does NP, non-deterministic polynomial time, mean? These are algorithms where if I have an answer, so if I have an answer, I can provide you with some extra information. If the answer is yes, I can provide you with some extra information such that I can easily check my answer or verify my answer. This is an intriguing concept. Let us give you some examples of algorithms where it is easy to verify an answer. All right, let us start with factoring. We all talked about how factoring was hard. Okay, now suppose I gave you a number n and I wanted to know about the ith bit of the smaller factor of n. Let's say it's an RSA number, p times q. So it's an RSA factoring problem. Okay, it's given to be an RSA number, p times q, and I want to know the ith bit of the smaller factor, p. Okay, is the ith bit of p equal 1? No, otherwise. Well, with an yes answer, I can associate some extra information. What is this extra information I can associate? I can actually give you the number p itself. I can give you the number p itself. When I give you the number p, if you are interested in checking my answer, you can first check whether p divides n. That's really easy to check. I can just do a division. Division is very easy to do on a computer. Then I can check whether the ith bit of this p is an actual 1. Okay, so here is an example of a problem where even though I tell you that the answer is hard a priori, there is little bit of extra information. If I gave you that extra information, you can easily check the answer. Let me give you other examples. Okay, so let us take an example of given a graph, like a weighted graph, G. So it's a graph where the edges have weight. Okay, and given a source vertex and a destination vertex, I can ask the shortest path, decision version. I ask the question, is there a path from S to T of weight, path weight, less than or equal to W? So I can ask you the question, is there a path from S to T of path weight less than or equal to W? So here is the shortest path decision problem, yes or no, given a graph G and W. Okay, all right. And here with the answer, I can always, with a yes answer, I can always give you the path. I can always give you the path, and you can verify that the weight of this path is less than or equal to W, right? So this is an example of what is called a certificate. Okay, with a yes answer, I can always give you a certificate. What about a no answer? Well, unfortunately, with a no answer, I can't give you a single certificate, right? I can't convince you that all paths this is not easy, not easy. I can, but in a different way, but this is not easy, all right? So this is an example of a problem where the yes answer has a certificate. Now what about the other way around, longest path? Okay, is there a path from S to T of weight greater than or equal to W such that no node is visited more than once? Is there a simple path that does not visit more nodes more than once? Now this is also an example. W, we call this the longest path problem, longest simple path problem. And here, yes, I can give you a path. Okay, no, there is no easy way to give a certificate. Okay, so there is no way to give a certificate, but at least with yes, with the yes answer, there is a certificate that comes with it. Okay, so these are problems where the yes answer comes with a certificate that is easy to check. All right. Now, this is a very, very interesting concept that the yes answer comes with a certificate, and this certificate is easy to check. What does it mean, easy to check? Which means that the check itself can be done in polynomial time. Okay. For example, if I've given a graph and a weight W, and I gave you a yes answer with a certificate, which is a path, how do I check that the yes answer is correct? Well, first I check that it's an actual path in the graph. Is it a true path in the graph? Do the edges in the path actually exist in the graph? Second, is every vertex visited? Is any vertex visited more than once? Check that. Third, is the total weight of the path greater than or equal to W? I can check that. These are all very easy checks. It can be done in linear time in the length of the path. Okay, so what is an problem in NP? And these are called non-deterministic polynomial time. What does non-deterministic mean? I will explain this briefly a little bit, but really this is a very deep concept and I have to do a lot of explanation for this, but I'll explain this later. But take my word that these are called this is the technical name for it for now, and we call them NP problems. Okay, in NP problems, you have a problem where you have an input, you still have a yes, no, but with the yes answer, I can actually provide you with a certificate which can be checked easily in polynomial time. The problem itself may be hard. Okay, so as an example of problem in NP, I've given you the factoring problem, I've given you the longest path, the shortest path, and so on. All right. So NP is a very important class of problems. So we have fast problems, which are polynomial time. Okay. So these are problems called polynomial time problems. Example, shortest path problem. Okay. And we have looked at other examples. We said primality testing was an example here. We said, problems involving arrays, medians, problems involving paths in graphs. The cycle problem, is there a cycle in a graph? So these are all problems in P. What are problems in NP? First of all, every problem in P belongs to NP. Why is that? So if you have a problem that's already fast, you have an input, you have a yes answer, you have a no answer, and let's say solving the problem is already fast. Well, then you don't need a certificate. The certificate can simply be empty, and you can run your fast polynomial time algorithm to solve and check. Okay, so you don't need to check the problem separately. If solving the problem is itself fast, you can easily check the problem. Okay, so every problem in P belongs to NP, and this is almost trivial. This is not even like a deep observation. This is trivial observation that just follows from the way we defined it. So this is almost like a trick. The way we defined it, because a certificate can be checked in polynomial time, if you can already solve it in polynomial time, then just solve it again with a trusted implementation. So make an implementation that you really trust, and solve it again and check the answer. Okay, so there is no need for a separate certificate to really check the answer. Okay, so every problem in polynomial time belongs to NP. Okay, now are there problems that are outside of P that belong to NP? Okay, and this is an open question for the last 60 years in computer science. It's what's called a $1 million problem. And this asks the question whether everything in P is the same as NP, which means that are there problems outside of polynomial time that cannot be solved in polynomial time, but whose answers can still be certified in polynomial time? Okay, let's take an example. What are such problems? Okay, so there are some problems here, okay, which we think there are problems which cannot be solved in polynomial time, but whose solutions can be checked or certified in polynomial time. Okay, as an example, we looked at factoring. Where the certificate was one of the factors. If I told you one of the factors, then it's very easy to check the answer. Okay. Likewise, for the shortest path problem and the longest path problem, we gave you certificates. Okay. So coming up, we will look further at this class of problems in NP, and we will have to look closely at what does it mean for a problem to be in NP, what does it mean to have a certificate, and then we will look at reductions between problems. Coming right up. Okay, so in this lecture, we are going to look at some definitions and examples of problems in NP. So let me first define NP. So we have problems that can be solved in polynomial time. And we define a superset of this, maybe a superset, we don't know. Okay, and this is an open problem, and let's call these problems P. Okay, NP is the set of problems which we don't know whether there is a polynomial time solution, but we know there is a way by which if you have an input, you have your output, then there is some extra information called a certificate that can be checked against the input in polynomial time. Okay, so checked against the input in polynomial time. Only for a yes answer, not for a no answer. So not necessarily for a no answer. The certificate is known only for the yes answer. Okay, and that's by the nature of this. All right, and there are problems. There is a class called co-NP where the certificate only exists for the no answer but not the yes answer. Okay, I'm not going to go deeper into that. I'm just going to talk about NP. All right, very good. So let us give you some the formal definition of NP. Okay, so formal definition of NP is a problem is in NP if and only if there exists an algorithm called the certificate algorithm Okay, there exists an algorithm called the certificate algorithm, so that for all x, if x gives, for all input x, okay, for all input x, if x gives an answer of yes for original problem, okay, so if x gives an answer for yes for the original problem, then what? There exists a certificate y such that, number one, the length of the certificate is some polynomial in the length of x. So length of certificate is polynomial in length of x. Secondly, the certifier takes in x comma y and returns yes. Okay, this is kind of a convoluted statement, but hopefully with examples it starts becoming clearer. But let me highlight both problems, both parts of the definition. So here is our original problem. If you have an input that gives you an answer yes, then there is a certificate corresponding to x, let's call it y, such that the certifier for this problem will give you yes. Okay, so if an input gave you yes, then there is an extra certificate that you can tack on such that the joint original input and the certificate together makes the certifier go yes. If the input was no, so if the input was no, then no possible certificate that you can tack on will give you an answer of yes. Every certificate that you tack on will always give you an answer of no, which means yes means there exists a certificate whose length is polynomial in the length of x. No means no possible certificate exists. And the certificate can be furthermore verified using a certificate or a certifier algorithm which is known to run in polynomial time. Alright, so this is the definition of NP. So to highlight this definition, let me first give you some prototypical examples of problems in NP. So let me start with a simple problem we can all wrap our heads around. Let's call this the graph 3 coloring problem. I give you as an input a graph, an undirected graph. Let me take an example. So here is a graph, okay, and I ask the question, can I color each node one of 3 colors, red, green or blue, such that no edge connects 2 nodes of the same color. So can I color each node one of 3 colors, red, green or blue, such that no edge connects 2 nodes of the same color? Okay, so here is an example and here is the coloring. So suppose I go red, green, blue, red, blue, red, okay, green, red, blue. So here is an example coloring. Okay, here is a coloring. I have colored successfully with 3 colors, red, green and blue, and notice that no 2 nodes have, no edge connects 2 nodes of the same color. Every edge connects 2 nodes of different colors. Alright, so here is Another example. Okay, here is another example. Okay, now it's very hard to convince you, but I will try that if I tried any way to connect red, green and blue, this, let's call them 1, 2, 3, 4. If you look at 4 has a connection to 3 different nodes. And if I color them through 3 different colors, there is no color that I can use here. Okay, so this is an example of not 3 colorable. Okay, so a classic problem is given a graph, vertices and edges, given the encoding of a graph, say yes if it is 3 colorable and no otherwise. If it's not 3 colorable, say no. Okay, now this is an example of a problem in NP. Why is 3 color in NP? Very simple. I can give you a certificate. To go with the yes answer, I can give you a certificate. What is the certificate? Well, I can give you the actual set of vertices and the color that goes with each vertex, and that's my certificate. V2, green, V3, blue, and so on. So I can give you the certificate, and the certificate is simply the color assignment that goes with the yes answer. Now, what's the size of the certificate? Well, if there are n vertices, the size of the certificate is just theta n. You are just associating for each n whether it's red, green or blue. So it's just 3 bits of information with each vertex, so let's say 3n. Okay. Now what's the complexity of the check for the certificate? So how do I verify the certificate? Number 1, verify that every vertex received a color. Every vertex received a color. And this color has to be a red, green or blue. Check. Number 2, check that for every edge, the colors associated with the vertex at either end are different. Okay. And what is the complexity of this check? Well, if the graph has V vertices and E edges, then the checking can be done rather rapidly, fast. Okay, so this is an example of a problem where along with the yes answer, I can give you the coloring that goes with the yes answer, and I can check quite rapidly that it's a true coloring. With a no answer, on the other hand, I cannot give you an easy certificate. Okay, so with the no answer, I don't give you a certificate. I only give you a certificate for the yes answer. And that certificate can be checked in polynomial time. Okay, so here is an example of 3 color problem. And by the way, is there a polynomial time algorithm for 3 coloring? No. Can I solve this problem in 3 coloring? Unfortunately not. The best known algorithms for 3 coloring are all exponential. Okay, the best known algorithms are all exponential. No one knows of a polynomial time algorithm for 3 coloring. And there is no reason we know to believe such an algorithm cannot exist either. So we are not sure. Is it a limit? Is our ingenuity, our imagination, our abilities not good enough to find an algorithm? Or does such an algorithm not exist in the first place? We don't know. Okay, so here is an example. Let me give you a few more. So let us take one other example, and this is called the satisfiability problem, or the Boolean satisfiability problem. The Boolean satisfiability problem says, suppose I had a Boolean formula involving variables x1 through xn, like x1 or x2 or not of x3 and x1 or not of x2 or x3 and x4 or x3 or not of x5. And I want to know, is there a truth assignment that makes this formula true? Okay, and this is the OR, the V is the OR, remember, and this is an AND. Okay, and a formula written in this form is called a conjunctive normal form. Okay, and this is going to be and each of these is called a clause, and you have an AND of clauses. Okay, so in this example there is a truth assignment. If I make x1 to true, if I make x4 to true, x2 can be anything false, x3 can be anything false, and let's say x5 is false. So if I set the variable x1 to true, x4 to true, x2 to false, x3 to false, x5 to false, then the entire formula is true. Can you check that? Well, true or false or true. So the first clause evaluates to true. So x1 or x2 or not x3 is true or false or not false, which is going to be true. The second clause is x1 or x2 bar or x3. That's going to be true or not of false or false, which is going to be true. The third formula is x4 or x3 or x5 bar, which is going to be true or false or not of false, which is going to be true. So each of these clauses is true. The entire formula is true and true and true, which is true. Okay, so here is a truth assignment that makes the formula true. Now there are formulae where no matter what truth assignment I use, they are never going to be true. So for example, x1 or x2 bar and x1 or x2 and x1 bar or x2 bar and x1 bar or x2. Now if you look at it, no matter what I set x1 or x2 to, so there are 4 possible truth assignments of x1 or x2. No matter what I set x1 or x2, there is no way to make the formula true. So the SAT problem is given a Boolean formula say yes if there exists a truth assignment to make it true, and no if there is no truth assignment for the formula. Now what is the certificate? Well, the certificate is the truth assignment. The certificate is the truth assignment. What is the size of the certificate? Size of the certificate is just the same as the number of variables. So size of the truth assignment certificate is polynomial in the problem size. In problem size. Now what about the other thing? The checking the certificate. How do I check the certificate? Very simple. I just plug in the truth values and evaluate the formula. So checking is simply plug in and evaluate, and that can be done rather fast in polynomial time. That can be done in fact in theta n, for where n is the size of the formula. Alright, so checking is easy, but coming up with the certificate in the first place is hard, because if you have a formula with n variables, so if you have a formula with n variables, how many truth assignment does it have? Well, it has 2 to the power n possible truth assignments to check. So running through each truth assignment and checking is not practical. Is going to lead to an algorithm that's exponential time. And in fact, that is the best known algorithm. So that those are the best known algorithm for SAT. No one knows anything better than doing the brute force. Okay. But if an answer is known, it can be checked quite easily. So SAT is an example of a problem that is in NP. It is in NP because it has a certificate, but I don't know if it is in P. In fact, 60 years of searching for an algorithm has not led to a definite answer whether SAT is in P or not. Most likely it's not. Okay, and that's our suspicion. But we don't have a proof of that suspicion. All right. So we have seen a couple of examples. Let me walk you through a third example and define the problem of P versus NP. Okay. The third problem that I would like to define is the traveling salesperson problem. Okay, traveling, and this is a very, very practical problem. Okay, traveling salesperson. So what's a traveling salesperson? Imagine I have n locations in a city, and imagine I have roads connecting these locations. And I have a depot. I have to start from my office. I have to visit each of these n locations exactly once. Okay. So visit each of these locations exactly once and come back to where I started. Okay, and every edge in this graph has a cost. Okay, and I give you a budget B. Okay, so the total cost cannot exceed my budget. Is it even possible to tour the graph under the budget B? Okay, so the inputs to this problem are the graph G and our budget B, and the output is yes. If there exists a tour, okay, under budget B, no if no tour exists. Now, what is the certificate for TSP? Well, the certificate for a yes answer is very simple. It's the sequence of vertices and edges that I visit. Okay, it's just the sequence of vertices and edges that I visit, and I have to come back to N1. All right, let's say if there are k vertices, then I have to come back to the starting point. Now, how do I check this certificate? First of all, the size of the certificate is just linear in the size of the graph. I have n vertices. I have k vertices. My certificate will have k vertices. It will have k edges and k weights. So it's not going to be more than linear time the size of this graph. That's good. Now, what do I have to check given the certificate? Number one, I have to check that every vertex is visited exactly once. Starts and ends at the same point. And sum of the weights is less than equal to the budget given. Okay, so if I have these three, then I can certify that my tour is indeed a good tour and my yes answer can be certified. All right, so this is an example of a problem in NP. But the brute force algorithm needs to go through every way of ordering the vertices, every order in which the vertex can be visited, and that's the brute force. N factorial, which is something like 2 to the n log n. Okay, and the problem is we cannot really get much better than 2 to the n for this problem. Unfortunately, best known algorithms are exponential time on the size of the graph. And this is such a practical problem. Like FedEx, if you can solve this problem very nicely, FedEx, UPS, all the companies that needs to make deliveries will be super interested. Amazon, all these companies will be super interested in your solution because it's going to save them a ton of money. It's going to save them a ton of fuel. It's going to save them a ton of time because they have to make circuitous deliveries every single day. Okay, a lot of people are going to save a lot of money if you knew how to solve this problem properly, but most people don't, and people can give you lots of money for even like good heuristic solutions, but even the best way to solve this problem currently known is exponential, but it's an NP, which means that if I gave you an answer, yes answer, and I gave you the actual tour, you can easily check that. So given an answer, I can easily check, but finding the answer is difficult in the first place. Okay, now let me conclude this lecture by briefly mentioning what is the meaning of non-deterministic polynomial time. What does this mean? So this is the name we gave called NP. So what is this non-deterministic? Well, the idea is simply this. If you can give your computer the option to guess. What does it mean? Suppose it has a magic way to guess between a 0 or a 1. So given the input to a problem, let's say the computer can guess the certificate. Okay, and let's say it gives it to the certifier, certificate verifier, which tells you yes or no. All right. So let us say you're given your computer this extra power of clairvoyance, which means that it can actually guess this certificate. So let's say you have a clairvoyant computer. Okay, a computer that has this magic power that it can actually guess some extra number of bits to make this certificate verifier say yes, or fail and say there is no such guess and say no. All right. Such a computer is called a non-deterministic computer. So it augments the power of existing computers to give non-determinism. All right. Is non-determinism even possible in the current state of the art? Well, it's kind of possible to simulate non-determinism. The way you would simulate it is run through all possibilities. Exhaustively. That's the only way we know how to simulate non-determinism on a computer, on a classical computer. By the way, quantum computers have a little bit that takes us towards this idea of guess. Okay, so classical computers, the computers that you and I are used to, are not able to do this guess, but quantum computers in a limited sense, in a very limited sense, we will see this next week, have the guessing power, some kind of a guessing power. Okay, let's just call it that. But if you imbued your computers with this ability to guess, then they can solve this problem in polynomial time. Why is that? Because they can magically guess the certificate, and we can check the certificate. And if the guesser succeeds, then you have your answer yes. If the guesser fails, then you know that because the guesser is like an all-powerful guesser, if it had known an answer, then it would have succeeded. Therefore, you know that the original problem answer is no. It's kind of a very convoluted thing. But if you think about it, it's rather simple. If you have an oracle, let's say you have an all-powerful wise oracle, and you can consult them with your TSP. You give them a graph, and let's say they immediately come back and give you the certificate, the tour. Then you say, well, my oracle found this tour. Let me check whether this tour is correct. Yes, it is correct. And therefore, I know that my original problem, TSP, has a tour under budget. On the other hand, if the oracle just remained silent or the oracle gave you a wrong answer, then you knew that your oracle being all powerful, if there was a right answer to be found, your oracle would have given you the right answer. And therefore, the original problem had to have the answer no. Okay, and that's how a non-deterministic computer operates, much in the way of like an ancient Greek oracle that gives you answers that you can check and verify. All right, and that is the reason why we call it non-deterministic polynomial time. It's polynomial time on a non-deterministic computer that's capable of guessing. The only way we can do guessing in our practical real world is run through all possibilities, starting from 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, 1, 1. Unfortunately, there are 2 to the power the size of the certificate, which is 2 to the power the size of the input to the power c guesses. So doing this guess and check gives you an exponential time algorithm. Okay, so every non-deterministic polynomial NP algorithm is, every problem in NP has an exponential time algorithm. The question is, does it also have a polynomial time algorithm? Okay, so we will explore these concepts further in the very next lecture, where we will talk about this magic concept called NP completeness. All right, coming up very next lecture. See you then. Okay, so now that we have seen the notion of what is a problem that belongs to NP, so the picture is we have problems that belong to NP. As a subset, we have problems that belong to P, polynomial. Okay. Now we are going to look at some very special problems in NP. Okay, very special problems in NP, and these are called NP complete problems. Okay, and these are very special problems, and these problems are going to be the key to understanding NP. Okay, and this is going to be very interesting. Okay, and interestingly enough, what we are going to do is we are going to relate problems. So we are going to relate problems, and we are going to compare whether one problem is hard as hard or harder than the other. Again, the idea comes from the notion of reductions between problems. Okay, suppose you have a problem A, which takes an input instance for problem A and gives you, and you want the answer yes or no. Suppose you have another problem B, which gives you input of size B, yes or no. Okay, now often enough you can ask the question, can I use B as a subroutine to solve A? And we have done this a lot. We have taken a lot of problems in our assignments, converted them to graphs, solved the shortest path problem, and used the shortest path to answer our original problem. This we have done a lot. Converted one problem into another and used the solution of the second problem to answer the first problem. Okay, and this is formalized in this idea of reduction. So what's a reduction? So a reduction from problem A to problem B. So a reduction from problem A to problem B takes an input to problem A and converts it to an input to problem B, such that if I can solve B, then I can treat this entire procedure as an algorithm for A. So the algorithm for A is simply take the input to A, convert it to an input to B, and use B to solve it, and convert the answer for yes or no for B into the same answer yes or no for A. And this is super important. I don't want to change the answer. The answer for B must be the answer for A. Okay, and this is called a reduction from A to B. Now if this converter runs in polynomial time, if it runs in polynomial time in the size of the input, then this is called a polynomial time reduction. Okay, so this is called a polynomial time reduction. All right, and we have seen plenty of examples of polynomial time reduction. Okay, we have seen plenty of examples of this throughout our algorithms class, where we have asked all kinds of crazy problems, and you've been asked to build up a graph, solve DFS or BFS on the graph, use the BFS or DFS information to answer the original problem, right? We have seen plenty of examples of this, and these are called polynomial time reductions. Okay, and the important thing is, if I can take problem A and reduce it to problem B, then these are the things that I can conclude. What are the conclusions I can draw? If there is a polynomial time, and by the way, I'm only going to talk about polynomial time reductions where the time taken to convert the input, okay, the time taken to convert the input can only be polynomial. If you allow exponential time reductions, you kind of trivialize things. Okay, things can be made so trivial that the input to B can be the answer to A, yes or no, and B simply is going to be the repeater. If the input is yes, it will say yes. If it's no, it will say no. Then the reduction should not be allowed the power to solve the original problem. Okay, so that's why I'm only allowing polynomial time conversions that can be done fast. Okay, so if there is a polynomial time reduction from A to B, and B can be solved in polynomial time, then A can be solved in polynomial time. Okay, this is very, very straightforward. We already saw this. If you can convert from A to B in polynomial, and you can solve B in polynomial, then here you go is a polynomial time algorithm for A. So if B has a polynomial time algorithm, then A has a polynomial time algorithm. So if I can reduce from A to B, and B can be solved in poly, then A can be solved in poly. Okay, very good. On the other hand, if I can reduce from A to B, and A cannot be solved in polynomial time, there is no way to solve A in polynomial time, then B cannot be solved in polynomial time either. And this is a super important observation. It is just the contrapositive of the previous observation. Because if there is no way to solve A in polynomial time, and suppose you came up with a way to solve B in polynomial time, then you're contradicting, right? You're deriving a contradiction. So therefore, if you can reduce in polynomial time from A to B, and A is known not to have a polynomial time algorithm, then B is also known not to have a polynomial time algorithm. Okay, so reduction works in the following ways, right? So if I know positive things about B, then I know positive things about A. If I know negative things about A, I know negative things about B. Many students confuse the directionality. So bad news flows this way. If I know bad news about A, then I infer bad news about B. Bad news being that A cannot be solved in polynomial time. Good news follows this way. If I know that B can be solved in polynomial time, then I know, so if I know already that B can be solved in polynomial time, I infer that A can be solved in polynomial. So good news flows in this way, bad news flows in this way, okay? And so you have to understand this, and bad news being that I cannot solve a problem in polynomial time no matter how hard I try, and good news being that I can solve a problem in polynomial time. So understanding the two basic properties of reduction is super important. Okay, so before I give you an example of a reduction, let me talk about an NP complete problem. So a problem is said to be in NP complete. So let's say a problem P is said to be NP complete if, first of all, let's not use P. P stands for polynomial time. Let's say A. A is NP complete. NP complete if, first of all, A is in NP. So A must belong to NP. Okay. And every problem in NP is polynomial time reduced to A. So which means that from every problem in NP, I have a reduction in that can reduce it in polynomial time to this problem A. So what does it mean? In response to this P versus NP question, if I have this magic problem A, which is NP complete, then if A can be solved in polynomial time, then I know that P must be equal to NP. Why is that? Because every problem is polynomial time reducible to A. Every problem is polynomial time reducible to A. And therefore, if A itself has a polynomial time algorithm, then any problem in NP can be done this way. Input to B, I convert it to input to A, my NP complete problem. I use my algorithm for A to answer the problem, and this can solve any NP problem B. Okay, so therefore, using this reduction, if A can be solved in polynomial time, every problem can be solved in polynomial time, and therefore P must be equal to NP. Now, if A cannot be solved in polynomial time, no algorithm can solve A in polynomial time, then P is definitely not NP. Why? Because A will remain outside P and definitely not be in NP. So A will belong to NP, but A will not belong to P. So therefore P not equal to NP. Okay. So once I identify NP complete problems, I don't know if there are any, but if there are such problems, NP complete, NPC problems, then all efforts can be directed to solve them. To solve or understand them. Right? If you study them and you study them a lot, then you can say anything about every problem, every imaginable problem in NP. That's the good part of it. Now, what's the good news and the bad news? Good news is we know of NP complete problems. In fact, and you would be surprised and you should be surprised, there are NP complete problems. In fact, there is no one NP complete problem, there's a constellation of NP complete problems. Okay, there's a ton of NP complete problems, not just one. It fills many volumes of a book. In fact, there's a famous book called Computers and Interactability by Gary and Johnson. It's filled with NP complete problems, filled with NP complete And that's the gist of it, right? So the whole thing is there's no one NP complete problem. There's a ton of NP complete problems. And by the way, if you have NP complete problem 1 and NP complete problem 2, because they are in NP, each problem must be reducible to the other. So there must be a reduction from NPC1 to NPC2 and likewise from NPC2 to NPC1 because they are all in NP, and you know that everything in NP reduces to both NPC1 and NPC2. So everything in NP reduces to both these problems. So if there are two NP complete problems, not only do they reduce to each other, but everything reduces to them. And if you solve any one of them in polynomial time, any one of those thousands of known problems in polynomial time, then you solve all of them in polynomial time because you know there is a reduction from each one to the other. Okay, so what are these NP complete problems? Can we give you examples of them? And well, the first example that was found, and it's called the Cook-Levin theorem, says that a particular problem, and let me call this problem, and this is a very famous problem called 3CNF SAT, is NP complete. Okay, and this is a famous theorem by Cook and Levin, and it's called the Cook-Levin theorem. The proof is not difficult, but it requires me to introduce to you a notion of computation called Turing machines. It requires me to give you a translation from computations to circuits. So the proof requires a little bit of mathematical definitions and development, which we are not ready for in this class. But typically this proof is taught in a theory of computation class. It's definitely taught in a theory of computation class. Okay, and it's spends the entire semester building up the background knowledge, the definitions of what a Turing machine is, what are the properties of a Turing machine, how do you make a Turing machine run in polynomial time, what's a non-deterministic Turing machine, how do you do convert from Turing machines on to circuits, and then you get to this theorem. Okay, so it's not difficult, but it requires a series of steps that cannot be done in the course of a lecture. So let us take this as a fact. What does this mean? This means that from every problem in NP, there is a polynomial time reduction to this magic problem called 3CNF SAT. So let us spend some time understanding 3CNF SAT. And 3CNF SAT is typically the first prototypical NP complete problem. And the proof is to show that every problem can be reduced from in NP can be reduced to 3CNF SAT. Okay, so this proof was done the hard way. Okay, and this is called the Cook-Levin theorem. So what is 3CNF SAT? I'll explain the 3 in a second. The CNF stands for conjunctive normal form. We've actually seen this before, but I'm now going to define it formally. And SAT is satisfiability. So 3CNF SAT is defined by a set of Boolean variables, Boolean propositions or variables. Let's call them variables, if you will. x1 through xn. Okay, and I'm going to give you a Boolean formula phi, which is going to be in a special form. What is this special form? Phi is going to be an AND of clauses. So it's going to have a bunch of clauses, C1 and C2 and C3 and C sub m. Each of these is called a clause. And this is the AND operator. So the formula has an AND operator applied to a bunch m clauses. Now each clause C sub I is the OR of 3 literals. Okay, the OR of 3 literals, L1, Li1, Li2, exactly 3 literals, Li3. Each literal, and this is called a literal. So we have variables x1 through xn, clauses C1 through Cm, and literals L1, Li1, Li2. Each literal is either a variable or it's some variable or the negation of a variable. So it can be xj or not of xj. As an example, let's have the variables x1, x2, x3, x4, x5. Let's have the clauses c1 and c2 and c3 and c4. So n equals 5, m equals 4. 5 variables and 4 clauses. Clause 1 is, let's call it x1 or x2 bar or x5. Clause 2 is not x1, not x2, x or not x5. Clause 3 is x1 or x2 or x5. Clause 4 is x, let's make it x1 or x3 or x5, x1 bar or x3 bar, or let's call it x4. Okay, so these are our 4 clauses. Okay, so it's the AND of ORs. Okay, and a formula which is conjunctive normal form means that it's an AND of ORs. Okay, and that's called CNF. SAT is the satisfiability problem. I'll explain. 3 stands for the fact that every clause has 3 literals. Every clause has, let's call it exactly 3 literals, but we can actually handle, if it's 2 literal or 1 literal, we can actually handle exactly 3 literals. But if a clause just had 1 literal, let's say, for example, the clause C1, I just wanted x1 as a single literal, no problem, just write x1 as x1 or x1 or x1. Right? So if you had less than 3 literals, it's very, very easy. Let's just make it a single literal repeated 3 times works for us. All right? You're allowed to repeat literals that way. So every clause is exactly 3 literals. I have m clauses. I AND them. I get my formula. Now the satisfiability formula says, is there a truth assignment to the variables? That makes the formula, the entire formula, true. Okay, so 3CNF SAT is in NP. Interestingly enough, this is very easy to prove because we already looked at the proof of this. You just need to find out a certificate, and the certificate is the truth assignment. Okay, so x1 is true, x2 is false, x3 is false, x4 is true, x5 is false. I give you a certificate, and you can easily check this certificate in polynomial time. Great. And we already saw this. Okay. Now the interesting part is this: every problem in NP, according to Cook-Levin theorem, every problem in NP reduces through 3CNF SAT. There is a polynomial time reduction from everything in NP. For example, the RSA factoring problem reduces to 3CNF SAT, which means that if I can solve 3CNF SAT fast, then I can actually factor RSA. I can break RSA rapidly, right? So you can now start to see where is the power of this problem coming from. Every problem in NP by Cook-Levin theorem has a reduction to 3CNF SAT. The TSP problem, the traveling salesperson problem, which we saw in the last lecture and we claimed was so important to FedEx, to United and so on, can be solved can be converted to 3CNF SAT, which means that if you can solve 3CNF SAT rapidly, then the TSP problem can also be solved rapidly. And that's good news for some people. Whereas it's bad news for RSA, it's bad news for privacy on the web, right? So there is both good news and bad news to this. So bad news and good news, right? Good news is lots of things can be done efficiently. Bad news is crypto, secrecy, privacy on the internet as we know it is dead. And 3CNF SAT, question is, can it be solved in polynomial time? And the entire P versus NP question hinges on this. And so far, we simply do not know. That's the best answer we can provide. We do not know whether 3CNF SAT can be solved in polynomial time. Okay. Now, interestingly enough, knowing that 3CNF SAT is NP complete, I can now do a reduction from 3CNF SAT to some problem, to some mystery problem A. If I did a reduction in polynomial time, then A becomes NP complete as well. Why is that? Because everything in NP reduces to 3CNF SAT, and if 3CNF SAT itself reduces to A, then everything in NP reduces in polynomial time to A via the reduction to 3CNF SAT. I can plug reductions one into another and get bigger reductions which are also polynomial time, and therefore A becomes NP complete provided I can separately show that A belongs to NP. Okay, so I need to show A belongs to NP, and if I can reduce from 3CNF SAT to A, then A becomes NP complete. All right, so now we are ready to do some more interesting NP complete proof. Okay, so now that we have done the hard work and note that 3CNF SAT is NP complete, let us try and prove something else is NP complete. So we will choose a simpler problem, and following the book we will show the problem of K-clique. What is a K-clique? Well, given a graph, okay, given a graph, a clique in the graph is a set of nodes such that all possible edges exist between them. So for example, if I consider the nodes that are shown in red, you will see that they form a clique. In this case, every possible connection exists between these four nodes. Okay, so this forms a 4 clique. All right, so a K-clique asks, given a graph G and a number K, is there a clique in the graph of size K or more? Is there a clique of size K or more? So this is a very interesting problem, right? So what does it mean to have a clique in, for example, Facebook? A clique in Facebook would mean a group of friends who are all group of people who are all friends with each other. Group of people who are all mutual friends. Okay, so cliques play a very important role in studying networks. Okay, in studying graphs, cliques play a very important role. So we would like to discover these cliques. All right, so then the problem of K-clique is it takes as an input a graph, takes as an input K, yes if there is a K-clique or no. And what's the certificate? Well, the certificate is the set of vertices that form the K-clique, right? So if I give you K vertices, that is the certificate. So the certificate is just K vertices. And I can easily check this certificate. How do I check this certificate? First, check that they are all different vertices. I don't cheat by giving you the same vertex again and again. Second, check that all K choose 2 edges exist. All pairs of edges exist in the graph. And that's it. All right. And that's how you solve the clique problem. And that's the certificate for the clique problem. And this shows that K-clique belongs to NP. Now, the interesting part is, how do I prove that K-clique is NP complete? To prove that, I have to reduce from a known problem. Okay, and what's the only problem that we know so far is NP complete? 3CNF SAT. So it's a known NP complete problem. Through the hard work of Cook and Levin, and I will find a reduction from that problem to k clique. Okay, I always encourage students to write this down, that I'm going to write your intentions down in the form of a diagram. I'm going to reduce from 3CNF SAT to k clique, and that means that my input is going to be a 3CNF SAT formula, and the conversion should result in a graph and some number k, such that if this graph has a k clique, then my original formula is satisfiable. If it does not, it's not satisfiable. Okay, so this is how I want to do it. So this is a reduction from SAT to k clique. How do I reduce? So let me take a formula with variables x1 through xn and clauses c1 through cm, m clauses, each clause being having three literals, li1 or li2 or li3. Okay.